Ma'am, shall we start, ma'am?
Okay, Priyadarshini.
Yes. Mohitji?
Yes.
Yeah.
Okay. I hope everybody can hear me. And first of all, good morning and thank you so much.
Sir, excuse me. I would like to say a few things about the workshop, then we can start the session, sir.
Sure.
Okay. Good morning to all. On behalf of the Department of Computer Science and Engineering, SSN College of Engineering, I welcome you all for the pre-conference workshop on data science Capstone, conducted as a part of our international conference on computational intelligence and data science, ICC IDS 2022. So data science is today's hottest business topics and an emerging field of science that has multiple aspects. It includes statistics, data visualization, deep learning, machine learning, business intelligence, data engineering, which all these topics are being the important topics in data science makes this topic an interesting and an interdisciplinary field. This workshop aims at providing insight to data science concepts. 3 sessions of this workshop with hands-on will cover the topics such as role of a data analyst, data engineer, and data scientist in data science project. And the first session will also have a discussion about linear, logistic, and multi-class classifications. And then the second session, we will come to know about the need for a multi-layer network, backpropagation, regularization, and optimization techniques. And in the third session, it's all about the research perspective in data science, and there'll be a walk through the notebook. Now, with this introduction, I request our HOD ma'am, Dr. T.T. Mrinalini, to share a few words.
Good morning to everyone. A very warm welcome to all the participants to this international conference workshop. So I would like to say a few words about SSN College of Engineering. Hopefully, most of the participants are not from SSN College of Engineering. As we all know, Sivasubramanian Adar College of Engineering is a reputed and highly ranked educational institution in Tamil Nadu. It stands out as a premier center for higher education with a mission of pursuing excellence in education and research. Within the scope of 25 years, SSN has grown to one of the top educational institute in the country, and it became an autonomous college 4 years back. And SSN College of Engineering, Computer Science of Engineering exists since 1996, since the inception of SSN College of Engineering. Department of Computer Science and Engineering offers BE degree program in Computer Science and Engineering, ME degree program in Computer Science and Engineering. Apart from that, we are recognized research center from Anna University to float PhD level program as well. Under this research center, we have so far 23 research scholars have graduated as doctorate from Department of Computer Science and Engineering, and currently 30 scholars are pursuing towards PhD degree. And excuse me, we have a dedicated and well-qualified faculty members. Among our faculty members, most of them are PhD degree holders, around 30 faculty members. And among this, 19 faculty are recognized supervisors from Anna University, so that other candidates from other private engineering colleges and those who are working in industry register as a PhD scholar under the supervision of our faculty, and they are proceeding towards their PhD degree. That's all about our Department of CSE. And regularly we organize the workshops, conferences, faculty development programs in the emerging field. And as we all know, Government of India is promoting these sorts of industry academia linkage. And also in recently, Government of India has floated this NEP 2020. There they are giving more stress on these sorts of emerging technologies. And as Priyadarshini told, data science today is the hottest business topic. Excuse me. And we in the CSE department always try to identify these sorts of hottest topic to bridge the gap between industry and academia, and also explore the emerging technologies. As the name of this particular workshop is the Data Science Capstone project, in this particular workshop, we will focus towards how do we build a data science application. As we know that today the scientific industry is, our scientific community is moving towards data science. All sort of scientific proof is through data. So knowingly or unknowingly, we all are doing all sort of decision making from every day-to-day activity based on data. Earlier, the science goes like that. The scientist will come up with a hypothesis, and just to prove that hypothesis, they will design experiments. They will come up with some mathematical models and just prove their hypothesis. That's how science has evolved. Now, altogether, the science has boiled down to data science. Once you have data in science, and if you want to prove some hypothesis is true, you can definitely do on that. So in this aspect, today's workshop, we all will learn towards how do we show our talent towards proving ourselves as a scientist in proving a particular hypothesis. So our today's speaker, Mr. Sharma from Ericsson, Bangalore, has come up with a wonderful package with starting from what is data science, how it differs from data science analysis and so on, till how do we do a project, real world project with a technology in the data science. With this introduction, I'll hand over this session to the organizers, Priyadarshini.
Thank you so much, Ma'am.
Thank you.
Now I would like to introduce the speaker for today's workshop. All the sessions of this workshop will be handled by Mr. Mohit Sharma. It gives me immense pleasure in introducing Mr. Mohit, data scientist, Ericsson, Bangalore. He completed his BTech in Electrical Engineering, Guru Shekhar University, MBA from Punjab University. He has completed a postgraduate program in Advanced Deep Learning from Indian Institute of Science, Bangalore. He is a data scientist with a demonstrated ability to deliver valuable insights via data analytics and advanced data-driven methods. He is also a reliable key advisor in driving business growth and revenue. It gains in customer loyalty and record-setting proof improvements. Problem-solving mindset and analytical approach is his forte. He has been pivotal in providing inputs into the collection of new data sources and the refinement of existing ones to improve the analysis and model development. He has to his credit several certifications in the field of AI and data science. Prior to Ericsson, he has donned roles in Microsoft, Wells Fargo, IHS Markit, and TCS. Mohit, it's a great pleasure to have you here with us. We welcome you. Thank you for accepting our invitation. Looking forward for an interesting session. We request the listeners to actively participate in all the sessions. Over to you, Mohit ji.
Thank you, Priyadarshini. That was a wonderful introduction. Thank you so much. So we'll start this session with the very first topic, wherein we will be talking about how the data scientist and what is the difference between a data analyst and a data engineer. There's a lot of overlap happens, which should not happen. That these roles are very well defined, but now the world of data science is exploding like anything, and when it gets difficult to hire the talent from all the perspective, it becomes important that each one of them know what the other person is doing, and there is a pipeline which in we all participate in a particular way. So what I'll do is we'll share a presentation wherein we'll talk about these three. Let me first share the screen itself. I hope, let me know once you are able to view my screen. And what I'll do is I'll just stop, probably minimize this and keep it here, right? So you guys can see my screen. Yeah. So what we will do is we'll first talk about, because it's a very wide subject, and my intention was that once I go through the notebook, there are going to be certain particular things which you will see. I wanted to make sure that you understand those things, and it becomes easier for you to even further go and make your progress in terms of reading and understanding what is exactly going on. So what I'll do is I'll touch upon very important abstract things. Maybe we will not have a discussion around why that particular thing is important, or why we are only talking about that one, or a discussion around that how this has come into the existence. But what we'll try to do is we'll try to capture those things. So first we'll talk about role of data analysts, data engineers, and data scientists. Then we'll jump into linear regression, logistic regression. In between these two things, first there is a concept of statistics, descriptive statistics and other things. There's a concept of hypothesis. We are just jumping them, and we'll move to linear regression and logistic regression. When we start this, I will start, instead of using a presentation, I will start using my digital pad, and I'll do more of a scribbling rather than just present, because we're going to talk about some mathematical notations and symbols. And then we'll talk about the need of multi-layer networks. I've just taken out the multi-class classification. I felt if you understand the logistic regression, it is not really difficult to understand multi-class classification. Then we'll directly jump into a first foundational step of why neural networks, right? So there is this question arise that why we are talking about multi-layer networks. Then we'll talk about backpropagation, because it is the soul of probably neural networks. Then we'll talk about why there are certain needs of, when people say regularizations, people talk about optimization. Within optimization, they will talk about momentum, EDAGRAD, RMS, and ADAM. And finally, we'll talk about the data science research perspective. There are 6 areas which I was able to identify, and we'll talk about why. So in this particular part, we'll come back again to presentation, and then finally we'll go to a Google Colab or my notebook, wherein I'll walk you through the example, and you should be able to identify all these things which we have spoken about or we'll be talking about, right? If you have any questions, please raise your hand and you can ask the question, or you can ping me the question, or maybe I'll take in between breaks and I'll ask if you have any questions for me, right? Okay, so far all good. So we'll move to the next slide, wherein the first question is, what is the difference between data engineer, data scientist, and data analyst? What does a data engineer do? And I'm starting with data engineer because he's the person who is first responsible for building, testing, and maintaining a data architecture. And he's also responsible for getting the data for a data scientist or for a data analyst from, generally there will be a main data source, and from there he will pick that data and he will bring that data to a more first layer of consumption tables, which we call. Probably there is almost all the organizations will have a main data source, and from that main data source we will have a further subsystems wherein we will have the data what is required for me, and all these responsibilities of building APIs for external services, enrich data, implement data warehousing goes with the data engineering. And engineers also need to refine the pipelines continuously to make sure the data is accurate and accessible. The very first layer where we collect the data is generally very messy. You can think of somebody who is, when you're swiping your credit card, or if an organization, if it's a retail organization, POC data wherein the point of sale data is being collected, it's going to be a massive data, and this just goes and gets with a very minimum data cleaning. It gets stored into a master data. From that master data, we will build certain pipelines, do some changes, extract some good information, get rid of unwanted data, erroneous data, and then we will save another database. So that's how the process is, and that's where the data engineer comes into the play. What are the skills required for a data scientist? I think SQL is the most used tool here. So ins and outs of SQL, which you should be aware of. There are database systems which one should be aware of as a data engineer, which come from, could be a Microsoft SQL, MySQL, PostgreSQL, and now these days the big data, which is very popular, wherein there is not really a structure to the data. It's not just rows and columns which we can use to store the data. For example, your uh, Facebook page likes, tweets which we do, documents, they cannot be really saved in one particular form of rows and tables. So what we do here is we will have NoSQL databases, MongoDB, Cassandra, Oracle, NoSQL. These are the databases which a data engineer is either expert in one of them or may know all of them. Then you have ETL solutions. A data engineer is expected to have information about the ETL solution, SAP data services, Informatica, segments, Stitch data, all these things. Data warehouse softwares like Amazon Redshift, BigQuery, Snowflake, all these are again some of the data engineering skills. Then you have coding ability. Now, earlier data engineers, like 5 or 7 years back, probably data engineers were much into SQL and all the top part of it. But with the invent of or coming up with of Python and the concept coming from the big data and programming tools like Databricks, Java, which was, so Databricks is built on Scala. Python is also becoming very, very popular for data engineers. What they do is they use Python, which is basically a PySpark uh, package, you can say, or a module which they use to deal with large data sets. Scala is like a very fundamental language. On top of that, you have a Python, wherein Python makes things easier for people to understand. It's an easy language, and gets you can, if you are a Python developer, you can pretty quickly pick up things and work with the data. And then finally, big data tools like, as I mentioned, Spark, Kafka, Hadoop, Apache Cassandra, and all those things. So what are the roles and responsibilities of a data engineer, which we, organizations will very fondly call it as DE? Develop, construct, test, and maintain architectures and processing workflows, build robust, efficient, and reliable data pipelines, develop solution for data acquisitions, ensure architecture supports business requirements, develop data processes for data modeling, mining, and production, drive collection of new data, and refine of existing data sources. And they also get involved in data reliability, efficiency, and quality. They need to ensure that the data which a business is asking for is of high quality, and it satisfies the rules which business use to process his data, right? Any questions from what a data engineer does? Okay, so we'll take the silence as no, and then we'll move to what does a data scientist do. Now, once you have this data, wherein you have the raw data, it was processed by a data engineer, then that raw processed data is what a typical, yes.
We have a question in chat.
Yeah.
Mr. Karthikeyan is asking how cyber security takes place in data security. How cyber security or takes place in data security?
Yeah. So Karthik, I think this is a little away from my expertise. Probably I'm not the right person to answer this question. But again, as I said, that it's there will be a security team, there will be an IT team which will be responsible for ensuring that the data remains safe, and it does not. Not everybody has access to that data, and I think that's what I can tell you for now. I hope that probably does not answer fully what you have asked, but that's what I can tell you for now. Okay. So data scientists are majorly involved with doing typically 4 things. One is cleaning and collecting quality data to feed to the training of the algorithms. You must have, as I said twice, the data engineer is also cleaning the data. They do a very basic job for cleaning the data. When the data scientist gets data, there could be a requirement for further cleaning the data and data quality check only solely from the training of the algorithm perspective. right? And then there is identifying the patterns within the data. That's a very important deal for a data scientist to understand what is the distribution of my data looks like, what sort of algorithms I have, what if there are any hidden patterns for, let's say I'm doing a classification problems for spam and non-spam emails, then what are the different parts looks like, what makes these two things different. So then build machine learning models, data visualization, although there is generally a data visualization team as well. If your product, if the thing which you're generating or is turns out to be a very big product, then you probably have someone from low code or pro code team members who will build a very fantastic dashboards for the visualization. But when I say data visualization as a data scientist, what I mean is whatever patterns you have identified, whatever analysis you have done, you should be able to present them through some simple charts. Could be complicated charts, but generally we prefer data visualization to discuss among within our team members and showcase the results for how the things looks like. And then refine business metrics by developing and testing hypothesis. So this is generally the pipeline. You will have the raw data, pre-processed data. You do your data science stuff. You get the data for the raw ML outputs. You build the model here. You do the post processing. There is something called as post processing as well, but we are not discussing here right now. It could be post processing is very much could be related to business and the solution to solution. And then finally you deliver your insights. Now, as a data scientist, what are the skills which are required? You should be, are programming Python, there is Scala, there are a couple of other programming languages. Ruby could be there. So these are some of the languages which are Java, C++. These are some of the languages which are very popular. But I think as a data scientist, when somebody is hiring, they are looking majorly for people to have these days, especially Python has become very, very famous, followed by R programming. But between Python and R, I think R is still considered as a more of an academic language rather than a full-fledged developer's deal. So that's majorly the difference which I could see. Then you have Hadoop. Knowledge of this tool is not always required for a data scientist, but if you have it, it's a nice to have or a mandatory thing. Then a mandatory thing, as I said. Then you have SQL. Again, it's not very, very necessary, but if you know an SQL, you don't really have to rely on a data engineer to go and tell every time that you need to fetch this pot of data. You can, simple SQL, queries, you can fetch the data yourself. But the table from which you will fetch the data should be prepared by a data engineer. He will extract data from the master tables and get you the consumption sort of tables wherein you can extract the data from. Then algebra, statistics, and ML is something which is the most strongest part for a data scientist. Then you have data visualization tools. You can have within Python also, there are too many modules which you can use for data visualization, but generally people will go with Tableau, Power BI. There are many other, I think I mentioned in data analyst because they use it a lot. Then you must have a business acumen. I understand that a lot of people think the data scientists are only working with the data, but until unless you have a business acumen, if you do not understand the business, how your business works, you will not be able to create features which explain your problem or which can help you solve the problems. And I'll tell you what we talk about when we say about the features. Let's look at an example wherein let's say there is a solution developed wherein you are traveling and you are traveling in France and you do not understand French. So what you do is you open your Google translator, you take a photo of it and translates those into English for you. Now let's say you have trained that particular model into with some fonts, some particular font, but when you go to France, they are using some different fonts altogether. Then the solution, then the answer which you will get, probably your model will not be able to read it or you will have certain errors. So if you do not understand that there are people who can be using different fonts, that's your business acumen. That's how you understand that, okay, there is a possibility of different ways of writing M, N, A, L, 1, 2, 3. So I should train my model on all these types of features. If that is not available, then I should create those features and train my model on that. Okay. And then the communication skills. And I think data scientists are considered to be very, very technical people, but if they fail to communicate their results to their managers, because they do not understand what is R value, what is P value, what is why you are saying what is that, but what is what. But so it becomes very, very important that you are able to convert your technical results into and are able to explain it to a non-technical person, and that's how you are able to sell your solution. It's not just only about writing papers. If somebody has written a paper, you take that solution, you understand that, you develop the algorithm, but then you have to help understand somebody, because ultimately it's going to be the business who is going to consume it. The roles and responsibilities include apply technical skills which you have learned from statistics, economics, optimizations, machine learning, deep learning towards the solution of important business problems. Utilize statistical approaches to build predictive models. Enable evidence-based decision making by extracting insights from structured and unstructured data set. Nowadays, we get a lot of problem statements from unstructured data. NLP is one of the fields which have grown miles and bounds, I think, out of 2015 and 2017 and 18, when Transformers, the Hugging Face people came up with fantastic algorithms like BERT, and there are many other algorithms which came into the picture. And a lot of organizations started working with unstructured data. Identify new and novel data sources. When I say new and novel data sources, what we mean is that you probably already had a data set, but as a data scientist, you should also think that what if you understand your business, if you have the business acumen, you can request that I think this sort of information probably will also have. Generally, there will be a business SME, and there will be a data SME, and there will be a data scientist who will come together, and they will say, okay, this is what I think. Do you have this information? Do you have this sort of information? And they will say, okay, yes, I can create this. Business will also participate, and they say, oh, if you're looking for this information, probably I do not have this information, but maybe some similar information I can help you with, so that you can develop your business insights and get more information about how this data looks like or works, or helps in predicting your problem statement, solving a problem statement. Explore new technologies and analytic solutions for use in quantitative model building development. Here is the major part wherein you talk about linear regression, logistic regressions, deep learning neural networks, LSTM, RNN. All these things fall particularly into this particular part. Design and develop customized interaction reports and dashboards. Once you have developed your model, you need to represent those to your, to the end business, to the people who will study it or use it. So generally, these are either in form of reports or in form of dashboards. Very rarely, you can also send them. There could be web APIs wherein they will be consuming it, or very rarely you can send your predictions or your outputs directly as an Excel file to your end user, and they ultimately I haven't seen, rarely I have seen that somebody just using an Excel file, but there will always be an interactive tool or a dashboard wherein they are consuming it or using it. Then help maintain and improve existing models. There are a lot of already built models. As a data scientist, you can end up into a role wherein you are asked to just help and maintain those particular rules, and probably enhance on top of that. Okay. So what, any questions from a data scientist perspective? So ML plays a very important role. Machine learning. So data science is about understanding your data and using the data, solving a problem. There are different tools to solve this problem. One of those tools is machine learning. One of the tools is statistics. One of the tools is your deep learning. One of the other tools could be, you might have heard about AI, artificial intelligence, which can be a simple if-else algorithm, which helps you solve this problem.
Mohit, sir, is there any common roles that are being played by data scientists and the data engineer? Because like the data pre-processing task, which has to be taken care by the data engineer, also should be it also should be evaluated by the data scientist. Is the understanding correct?
That understanding. So see, what is it when we talk about data, there are a lot of things happens when you collect the data. That data cleaning cannot be handled by a data scientist, because as I said, that if you can look at the skills, they're totally different for both the parties. So that skill is absolutely different, and it takes a lot of effort to create your data warehouses or your data for an organization, setting up those tables, concatenate those tables. There is a word for that, which we call as data modeling, which has nothing to do with data science modeling. which has nothing to do with quantitative model. That's why I particularly use this word quantitative model development. So that's a separate thing. But yes, I would say that there is a slight slight overlap between when you are working on a data science pipeline, wherein a data engineer helps you, or you can take that role as a data engineer and you can do that work. After the first set of pre-processing, table setting and all this has happened, when you get the raw data, then there is a slight overlap between them, but which is acceptable, but should not be too much. Somebody should not go and ask you, you go to the master table, extract the data and start solving the problem.
Mohitji, there is one question in the chat.
Yeah.
So what kind of role does ML play in data science?
Yes, that's what I answered. It's a very important, I would say in today's world, there are like 80% of the problems as a data science are being solved through machine learning algorithms.
Okay.
Yeah, it's just one part. Statistics was another part, and AI could be another part. Some algorithms like depth first search, breadth first search, they are also part of data science, wherein we solve particular sort of problems using those algorithms. But right now, ML is the most substantial part, I will say. And slowly, deep learning is taking its role when it comes to unstructured natural language processing.
Yes, thank you.
Yeah, thank you. Any other questions? Can we move forward? Okay, so I'll take this as no, and I will move forward. I will take this as yes rather than no, and I'll move to the next part, wherein what we talk about data analyst. Now it's very important. There's a lot of confusion for the data analyst, because data analyst, business analyst, these words go very close and close. And so there is a particular definition from a Technopedia data analyst for a data analyst. This says it's one who deciphers numbers and translates them into words to explain what data tells. Okay, so basically you have a data, you look at the data. It could be, let's say you have sales data for Coke and for Pepsi. They both are competitors. This person will look at those numbers from different angles, or aggregate them at different levels, and tell probably what does this mean for a Coca-Cola. Are they growing? Are they behind? Is there a possibility of learning something from Pepsi? What sort of promotions they did? Can we pick up some promotions? Which months they were very high, which months we are lagging, in which stores we are lagging, why we are lagging, all these sort of data things they talk about. So basically what data analyst does is he works with the current data and generally looks at the previous months of data. He has no role in, he can make some inferences about the future or how can you improve, but he does not make that inferences with certainty or that much confidence with the help of numbers. Okay, so that's what a data analyst does. So retrieving relevant data from various sources and preparing it for further analysis. So if you know about companies like Nielsen, companies like Kantar, what they do is they go to the end users and they say, if you give us your data, we will prepare those insights for you, this kind of insights I just mentioned. And that's where we are talking about this retrieving relevant data. There could be a lot of information, but if I'm talking about promotions, I should be able to extract only information related data. If I'm talking about, if I want to study only Pepsi, then I should be able to extract data for Pepsi. Pepsi has certain variants, I should be able to extract data for Pepsi variants. Okay, that's what this retrieval of data, relevant data for the analysis, kind of analysis which I want to do, should be retrieved. There are certain very particular name, market basket analysis, there is pricing analysis, and all these sorts of analysis which are done by the data analysts. Basis on the analysis, the data analyst needs to make conclusions and then complete reports and support them with visualizations. And along with reports, they need to explain what differences numbers mean when looked at from month on month or across various audiences. So that's what Jay Burnley generally talk about. They will talk about demographics, they will talk about trends, they will talk about which month was good for us, which month was bad. They will then try to explain you that why that particular month was bad. Is the market share eaten by my product itself, or cannibalization happened, or things like that. Okay, so I see somebody has said a red line for me here. So landing a data analyst job doesn't require a strong math background, to be very honest, but if you have knowledge of statistics, then you can be a really good data analyst, because some sort of hypothesis, um, or z-score, s-scores. They really tend to help you, like mean, median, when to use them, when not to use them, what are dispersions, different sort of dispersions when we talk about, where to use them, what does variance represents. All these things really help. Extrapolating the data helps if you are a statistician, if you have knowledge of statistics. And data pre-processing, visualization, ed analysis. And I think one of the most important skills for them is proficiency in Excel for a data analyst. So again, statistics, SQL is required, but I've not seen much people using SQL directly extracting information. There will always be a further one layer of tool which will be very easy. Generally, they will be embedded in Excel itself. You'll be able to extract the data quickly and do your processing. Microsoft Excel is very, very important here. I think data visualization tools like Tableau, Power BI, infographics, and Quick Insight. Business acumen is absolutely the most important skill, I think, along with the Microsoft Excel, and obviously the communication skills. This person should again be able to tell that what he is doing, how he is building that, and probably able to explain to the business that what business needs to do in terms of getting to a solution. Any questions? So these are the roles and responsibilities for DA: provide source to target mapping of the data sets, perform testing and validation of data sets, collaborate with leaders and managers to determine and address data needs for the various organizations, write and apply data quality rules, generate dashboards and KPIs. And most of the times they will be just kind of refreshing those reports. A lot of work goes on refreshing the reports, because once you have decided that these are the parameters I want to look for a particular business, every month or every bi-weekly or weekly you will update those reports. And then document structures and type of business data. But let's be very clear that this role is not something, I may have put it into the last, but this is not something which is an easy role. It takes a lot of effort to understand the business and what drives the business, and then following that, getting your insights into the which are useful for the business, because from the data you can get n number of insights, but you need to really understand that what is important for my business, what my business is currently facing as a problem, and looking at the previous month's data, how I can solve that problem. So this basically generally helps with the kind of secondary decision making for the business. Any questions we have? Okay, so I think this is how they all fit all together. Developing and maintaining databases, pipelines, development of machine learning algorithms and models. Okay, I think there is this development of pipeline for the machine learning algorithms and model, it should be, and data warehousing solutions. Here you collect and cleanse the data, sitting through the data, identify hidden patterns, build predictive models, prospective ML models, and refine business metrics by developing and testing hypotheses. And then finally, we just talked about data analysts, what they do. And there can be always a slight overlap between all three of them. So you can think of them a Venn diagram wherein some responsibilities always at the end of the pipeline can rely between each other, can have an overlap between each other. Yeah. So now what we'll do is we'll talk about linear regression, logistic regression, multiple, again, as I said, multi-classification I've actually removed. So what I'll do is I'll move to the notepad, and I'll just stop the video, because generally it takes a lot of two things. One is I get conscious. The second is it takes a lot of effort, lot of bandwidth. So I hope that is fine.
Yes, Mohit. Yes.
Okay, great. Okay, so what we're gonna do here is, and please pardon me for my handwriting, and I will see if I can. No, I cannot remove this line. If somebody who had put that line, if they can remove it, it'll be really, really helpful. So let's start with the linear regression. Right, linear regression. So what do we have as part of linear regression? We have some inputs, right? These inputs are generally represented by x1, x2, and so on up till maybe X dimensions, and you have n number of observations. So this is how you will represent, and this is a D dimension, and there will be a target variable which we probably will represent for now like Tn. For the this will be my target variable. Okay, somebody has a question. Let's see. Yes, Karthik, I think I'm gonna throw a lot of mathematical knowledge today. But when we talk about mathematical knowledge, what happens is that there is a question rises, why this, why that. I mean, given the time constraint, we will not be able to answer why this, why that. But what we'll do is you can always connect with me later, and I can probably help you understand that why we are talking about this. And there are theorems which we need to prove. There are some, you can say, toy examples which we can look into and solve the problem. But today, probably that mathematical knowledge, we will discuss a lot of mathematics, but we will probably not talk about why. So if I say x1, you have to agree with me that this is x1. If I make some statements, you have to agree to that, because we'll not be able to prove those statements. I hope that is fine. Okay, so so this is your target. So basically, if this is your target, then target represents generally your test data set. You generally have a training data set. Sometimes you can have a validation set, and then you have a test data set. Validation set and test data sets are almost similar. Only thing is that validation we use for hyperparameter tuning. We will come back to all these things once again, but that's for now. You can understand it like that. So test samples, you will represent test samples with probably T1, T2, and so on up till Tn for nth observations. Right now, what we want to do is we want to predict this T1, T2, Tn by understanding our input features. And how do we learn this? We learn this through a function. So there has to be a learning function. This learning function is represented by, let's say, f. It will have some parameters. Let's say these are theta parameters. And what we'll do is we will pass on these information points which we have into this, and this function should be good enough, or this function should be such that these parameters for this function should be learned such that using these features we should be able to predict our t value. Not exactly, but to be very close to t value. What does this mean is that if I know that what is my car's mileage, what is my speed, or what is my horsepower, I should be able to use that and say, or if I'm predicting mileage, then using my horsepower, weight, dimensions, car weight, all these things using, I should be able to predict the mileage for my car. If I'm talking about the mileage for my car, then if my car's mileage is 20, I am not expecting 20 as an answer. If I get 20 as an answer, that's fantastic, but I'm expecting somewhere closer number to 20. Okay, so that's what this means. This is what you intend to learn. Now, this, as I said, let me also write it here, that this is your parameters for the functions. Now, how do we learn these parameters is through something which we call as cost functions. And there are many different types of cost functions, and cost function can change based upon your learning problem. So let me just write this down also. Can change based on your learning problem. Okay, so is this setup clear, that you're going to have an input which will be represented by x1, x2? Generally it's called as independent variables. Then you will have a test samples which probably written by t. You have to figure out a function, or you can define, or you can say, okay, I'm going to use this particular function which will have some parameters. You pass your features into that function. You try to learn those parameters through a cost function and try to get to a t value, which is your prediction which you want to make. This setup is clear? If this setup is clear, then we can talk about first thing, which is linear regression. Now in linear regression, the prediction output, which is represented by yn, which is generally represented by y. So you will find a lot of books which will represent linear regression saying y is a function of x, like this. Okay, and this function is a linear function. That's what basically linear regression is all about. So technically, this y output which we're talking about can be written as w naught plus, you will have n dimensions. So let's say I is equal to 1 to d dimensions, and you will have your wi xi for that particular row, and you can think of n as a row or an observation. Okay, this is your prediction output, and we already talked about how your sample looks like. But in in linear regression, what we do is there is something called as bias. So your xn will look something like this: 1 comma x1 x2 so on up till xn. This is how it will look like. So this one is something which is an extra here, and then this particular thing which I wrote can also be written as y of n, and we take all the weights because it's going to be a matrix multiplication. So you have to do a transpose here for these weights, which will also look something like this. So your weights is a vector. It will also look like something like w naught comma w1 comma w2 up till wn, right? So you take wn and you multiply it with your xn. And please guys, it's been very long. I'm come from a lot of hands-on experience. Once you go into the job, you probably miss a lot of things. So if there is certain notations I write wrong or spell something wrong, or it's a theta, I mention it as eta, you please be patient with me. Okay, so this is what you do when this is what your question is here. Like, this is how you represent your equation here: yn to wt xn. Now what is a loss function here? If you guys have been working or have you heard about it before, what is the loss function for linear regression when you're solving? Anybody? Someone? So there are these parameters. What are the parameters which you want to learn here? There's just one parameter, which is w. W is what you want to learn here in this particular case. These are your parameters. Okay, so loss function which we have here is, which is represented probably by en, we will say, with respect to your w, will be what was your actual output minus yn of your, and we take a square of it. The reason we take square of it is again mathematical, but generally we'll take a square. That this we call it as squared error. Okay, and there is also another error which we take, which is just developed on top of it, which is called as mean square error. In that, what we do is we take all the observations, divide by, we take the kind of division by total number of observations. We say 1 total number of observations, we have en of w. Basically this part we will keep here. So this is your loss function. Any questions so far? So what we want to do in a linear regression, we have input values, we have a output defined, that this is how my output defines. There is w, which we, as I said, that there is this parameters which we have to identify, and I parameters are w. So the question is, how do we get to the optimal values for w so that we have a best solution? Yes. No, so if you have a polynomial, there can be a polynomial functions as well. There can be an exponential functions as well. There are many variants of linear regression. It's not just that you only have to work with the linear functions. It's just that it will become a non-linear problem. If you're so linearity is right, you have y square, x square, x1 square, x square. So this is also linear. But if your y remains same, one of the parameters x1 becomes x square, the other one you x cube, then it becomes a polynomial problem, and it's no longer a linear problem. Linear problem means that if I have a data set, it could look like this. But if I'm going to use a linear regression, it's going to just define one line. Okay, that's what a linear problem is. If it's if however my data does not look like this, and it sometimes look like, probably it goes up, then comes down, and then again goes up. This cannot be modeled through a linear regression. You obviously linear regression will give you a result, but you see that this is wherein you are not able to predict. You are not able to predict doing this will not do well for you. So what you need to do is you need to, in that particular case, we need to have a polynomial function wherein you will have something like this. Yeah. So, but this is a non-linear function now. I hope it answers your question. Okay, so I'll just pick up some pace here. And so the question is, how do we solve this equation? How do we get to the W? Now, one way to solve is through use of closed form solutions, but closed form solutions can sometimes be computationally very expensive and can be cumbersome to evaluate because of the amount of data which you are crunching. So one other way of solving that problem is through the gradient descent. And I will request that you guys please take notes in between, because all these terms, when you go to the notebook, you will see all these terms coming up. Okay. So what is a gradient descent? What we do is we say that we start with some initial weights. Start with some initial weights. Okay. Initial weights for your parameters. So let me write down parameters with respect to theta. And then you you use a formula and you update this theta. So you will start with some value for theta. Let's say at a given time tau +1. This is the next step which I want to do. I want to update my weights. So what I do is I take my current weights, which can be any randomly random numbers, or it can be 0, or generally it will not be 0. It will be a random numbers, but it will be a very small number to start with. Okay, and then you have a learning rate eta, and then you do the derivative of for W with the error with respect to W at this particular time. Okay, so this is the formula which we use to update my weights, my theta, and we keep updating until and unless we get to there's a concept of basically. So what is happening here? Let's just talk about. Let's just say you are in 2 dimensions. The idea is to figure out the minimum point or the optimal point. And it's why I have driven this convex, because convex problems are easier to solve. Concave problems can be difficult to solve. So what you do is, let's say you at the beginning you are here. What you're doing is you are trying to figure out in which direction you should move. Gradient basically means you try to get the slope, and you try to say in which direction I should move. And then once you have decided that which direction you should move, you want to move with a particular want to move particular distance, and that how much particular distance you should move is given by your eta, which is called as your learning rate. So let's say you will have, this is a fixed quantity wherein, and there is other ways of modifying this. Will come into that how either what is the problem with fixed quantity. There are the ways in which we do that. Everything has a one or the other problem. So how do we keep solving that problem? And you try to move in that particular direction. Okay, you keep moving until unless you have reached your minimum point. Now in this particular case, this is your global minima. But if you imagine 3 dimension, 4 dimension, 5 dimension, or maybe in 2 dimension also, you can have something like this, right? And if you are starting initializing your weight somewhere here, then you will, after this you will not move, because this is your minimum value and there is no slope after this, so you will get stuck here. And however, we know that the global solution is this one, global minima is this. Now there are again different ways of solving this, but what I am saying is that gradient descent not always gives you an optimal solution. It is not always that you will get into a global minimum. You'll be able to achieve the global minimum, but the point is that you will be able to get to the minima, which could be the closest possible best solution for us. Any questions in this? So if I go to my linear regression equation, this was my loss function. And this is basically resulting into not loss. This was my loss function, and this is the error which I'm getting from my loss function. So if I put this, how my I'll just go and directly write down the final answer here. So what we do is En with respect to weight for the weights is, as I said, that's going to be Tn minus Wt xn, and you are taking square of it. So if you have to take the derivative of this En for the weight W, then this will be your 2 will come down here, right? And then you have Cn minus Wt xn. This was for the whole thing. And then you have for the Wt, you will have, I think, minus xn, right? So this is your derivative function. And you put the values in this, you know the current value, you know what is your t, you know what is your x values, and you get the next value. You multiply it with your eta, you subtract it from the current W value, and you get your next W. So you know that where the slope is, and then you kind of move into that direction. Yeah. No, so there are different techniques in which you can try to move to the global minima, but it still remains a problem wherein you get stuck at local minima, and you probably will not know that whether there is a global minima available or not, because 1 and 2 dimension for experimentations, it's okay, fine. But when you're talking about huge data sets, when I say huge, a simple one photograph data could be a million rows. It depends on how, what was the number of pixels which you are using. So it can be very difficult to understand whether you are in a global minimum or the maximum, whether you have achieved that or not. But obviously statisticians are not easy people to give up, so they are trying to figure out further solutions wherein if you can avoid the local minimum, you can probably move towards the global minimum, and we will touch those topics as well. I hope this answers your question. Was there any other question? Great. Okay, so now sometimes what is there is that the function which you have used could be taking an average of the errors, could be taking the sum of the errors. If it is taking some of the errors, then everything which you have done here will look something, you at every step when you do this, it will look something like this, wherein you will sum up everything. If it's average, you will do average. But in our case, if you see, we are doing the sum, so it is going to be sum here, so it will be n, and then I think I have already written that, but again, just emphasizing on this, and then you will have W here, right? This is n is equal to 1 to total number of observations. So for each observation you do this, for the whole data set you do this, and you get your gradient descent value. But having said that, in Python you also have closed set of solutions which are being closed form solutions. But when your dimensions increases, that could be cumbersome. It can result into a lot of problem, time consuming basically. So how do we get to this? This is just one, it's not just one step which you do. You basically run it multiple times and select the best parameters. So this is probably an answer to your question, that how do I go to the local minima? So what you do is, every time you initialize your weights, these particular weights which I have said, I initialize with different values. So you land up on a different places, and then you can decide which one among them is the best solution. That could be one way of approaching and saying that how can I reach to my global minima. But still, again, it's not necessary that you will achieve your global minima, but this is multiple weights can be initialized, and for you can run the algorithm multiple number of times with different parts of the data, and then you can try to hope to get to the global minima. Generally this trick works, and sometimes it may not work. Okay, so now there is again, as I said, that everything has a problem. Even the gradient descent, if I talk about, it has a problem. What is the problem with the gradient descent? Maybe we'll write it right, GD. Problem with the gradient descent is that if your sample size grows exponentially, or if you have a very large sample size, and I'm talking about probably you have maybe 10 lakh observations or 5 lakh observations. It's a very, very large data set. You also have n number of dimensions to deal with. Then gradient descent can also become computationally expensive. Okay, this can also result into gradient descent for being computationally expensive. Okay. So the thing is that when we talk about gradient descent, it's not necessary to walk through all the data. Okay, and that's why there is a we have noticed, or you will notice, that most algorithms, they converge faster on approximate gradient estimates as well. So if we can somehow calculate approximate gradients, then there is a possibility of faster convergence. And when I say convergence, what I'm trying to say is that I want to reach to this optimal point. That's what we mean by convergence. So what we do is, to avoid this computational, although we have very fantastic, super fantastic things, I'll also show you the example. My machine, which I am right now working on, is 32 GB, and I have got a GPUs and some other things as well. So it's a fantastic machine which I have. But still, for I was preparing a notebook for you guys for today's walkthrough, and it was still taking 1 hour for one set of going through a gradient descent. So the data which I picked up for that. So it can be really problematic and can take a lot of time. So what sometimes we do is, we sometimes evaluate you sometimes evaluate these parameters using single sample. That means one observation at a time. And this is also famously called as, sometimes called as, online learning, or it can also be called as sequential learning. So when you pick one example at a time and you start learning through that one example, for every example you will go through, you will update your weights. Next example, you will update your weight. Next example, you will update your weight. That's called as single sample, or online learning, or sequential learning. In many online processes, this is being implemented, and people, every example comes in, people try to learn through that, update their weights, or basically have a learning for their parameters to get to keep improving their models. Okay. But there is another method which is, I think, is much more popular, is for the computing gradients. It's called as computing gradients is done on subsets. And these when you do a computational grading on subsets, then it is called as stochastic gradient descent, or stochastic methods. Okay, so basically what you do is, you are not going with one line at a time. What you're doing is, you are saying, okay, I will pick up some set from my training data set. So this is my whole training data set. What I'll do is, I'll pick up some set of this, and I'll use this to train my weights and I run on my gradient descent to get to my gradients. Okay. When you do these subsets, this term is, these subsets are called as mini batches. And batch is actually something different, but right now people use them again simultaneously. So this is sometimes also called as batch, but actual correct name is mini batch. But again, people have, there's very bleak line, people have started calling it a batch. Mini batch is the same thing. So we also going to use it as one thing, mini batch or batches. So mini batches, as I said, is nothing but the subsample or subset of the actual training data set. Now, if you, let's say you have n samples, and you decided to create each sample of certain size. Let's say your overall data set has got 1,000 observations, and you decided to create each sample with 100 observations at a time. So this will be your sample size. Then you know that how many number of times you have to, how many number of iterations it will take to go through the whole data set. How many times you have to go through, ensure that you complete your whole data set. How many such travelings, or you can say whole number of times you have to do that to go through. That will be n by m, right? Iterations to cover the to cover entire data set, right? Correct. Now this covering of the entire data set, or this one way going through the first batch, second batch, third batch up till the 10th batch and then coming back again, that whole process is famously called as epochs. This is a special word for that, epochs. So what is an epoch? When you cover the entire data set. When you cover the entire data set, that is referred to as epoch, one epoch. So what we do is, we will, again, as I said, that you have to run it some multiple times. What you do is you divide this data. You say, okay, I'm 110, so there will be 10 epochs which you want to run. You will take 10 epochs to go through the whole data set, but it's not necessary you have to do the 10. You can probably do you will do the 10 epochs, but then you can decide that how many times I want to repeat this thing. So that's a very famous concept when it comes to technically when it comes to deep learning, and that's why I'm talking about this. I hope everybody is clear about this. Any questions? And let me just also write specifically what is iteration. I don't think we should get confused. So iteration is number of gradient steps that you took, and let's say it's represented by probably L. So if you have n by m steps, then how many times you have taken those steps is L multiplied by n by m. So these many iterations you have taken when you are talking about the gradient descent for your mini batches. Now, how does this help me as in my day-to-day time, or when I'm trying to solve this problem, or knowing these numbers? One, through these numbers, I can calculate the training time it will take. I can calculate how much time it will take, because if I understand just one epoch, how much time it will taking, then I can identify, okay, for 10, how much time it will take, right? And it helps me then say, okay, my algorithm is going to take 2 days or 3 days or 4 hours or 2 hours. Based on that, I can commit to my end client, and I can further if I'm using a common resources like cloud or something, and my team also uses it, I can go back and tell them that, okay, please do not push anything which is very heavier, so that my process should not get impacted. Again, in the cloud also, we have a limited resource, right? So I think that's it. This is what we these are some of the terms which I wanted to introduce, and then we will move to from the linear regression perspective. I think you guys are aware of that. Okay, once we have done the y and we have identified the function f of x, then once you get the y results, which is predictions are represented by y hat, you have actual y's, then you need to say that how good or bad my model is. So that is called as model accuracies or model validations. So for doing a model validations, there are a lot of things, but particularly people use R square, which is called as coefficient of determination, adjusted R square. Then you have root mean square errors. Then you can have, sorry, S should be here. Then you have MAPE, you have MAE, MAE, and so on. There are many other things which there are global testings, there are cross validations and all the stuff. We are not touching them. These are some basic things. Yep. What is this? Okay, I think for the registration or something, is it? Okay. So far we are good. Any questions? Right. Okay. How do you choose the optimal value for epoch? So now there is this fantastic thing about data scientists. There are so many things which are all into experiments. You cannot say that what is the optimal number of epochs. You have to study your training error and the validation error, and then you have to decide what should be my optimal number of epochs. But again, that's a hit and trial thing. You have to experiment and you have to get to the number. What I meant was that data science is a fantastic subject, there is always a margin of error which we say. So let's say when I say my boss that I will predict this by 95% accuracy, then he also understands there's going to be 5% error in that. If I succeed, whatever I said, if I said that the organization will go by 10%, if I succeed and the organization grows by 10%, it's my credit. But if it does not, if it grows by 5% or 6%, then I say I told you that there's going to be a 5% error. So a lot of things are uncertain, and we just have to get through them through the experiments. Okay, any other questions, guys? Okay, so now what we'll do is, now that we have understood what is this, we will move to logistic regression. And before we move to logistic regression, I have to give you an introduction to the or maybe rather than if I say logistic regression, right? So before we talk about logistic regression and move into the complexities of the logistic regression, we need to first understand a concept of likelihood. Okay, and we will do this, understand the concept of likelihood or its interpretation first for the linear regression. Because once we understand the importance or how the likelihood falls into a linear regression perspective, or how we interpret it, then I think logistic regression becomes very easy, and it becomes digestible, and then there is multi-class logistic regression. Everything becomes very easy for us. So let's say we have a target value or a number which we want to okay, rather than saying like this, let me say it like this. If I say that you have to pick a number, you are in a setup and I say that you have to pick a number which will be my target number, then what would be the first distribution you will think that this number will come from? If I have to pick a number, generally most of the times, if I ask you to pick up a target value, then where do you think that distribution will come from? This number has to come from a distribution. Even if it's for most of the real examples, maybe let's say I want you to pick up a number for the weight. What will be my weight? What do you think my weight will be? So if you have to guess my weight and if you pick up a number, there is a distribution around it. What do you think the distribution would be? From which distribution this number will come from? No guesses? Okay, so most of the terms in statistics, the target value number or this value can be thought of from coming from Gaussian distribution. Okay, now when it comes from a Gaussian distribution, the target value, as I said, Tn, is, as we said, that this is coming from a Gaussian distribution, and Gaussian distribution will look something like this, sigma square, right? So this relates to a this term, this actually relates to identifying a squared error loss function. Okay, so what we are saying is that if this comes from this distribution, this my weight which we're talking about comes from this distribution, then what is the probability of having a Tn given your xn observations? Right, so what we are saying is I have some height, I have some other body, my muscle mass is there, my BMS is there, some other features are there, and then there is this weight which you wanted to predict, right? So I'm saying that given these features, what is the probability if you say that my weight is 80 kgs, which is not, but if you say that, okay, if this is 80 kgs, then what is the probability of me having an 80 kg weight given all these features? And we know that this distribution comes from a Gaussian distribution. So for Gaussian distribution, it will look like 1 upon under root of 2 pi sigma exponential, and then I'm just writing this term here, but this is an exponential term here, minus 1 by 2 t raised to the power n, and then wt xn. And because this is an error, we want to square this off, and then this will be sigma square. Okay, and this this thing which I'm talking about is giving me the likelihood. Okay, now when this is there, the likelihood, when we want to calculate this, what we generally do is mathematically it makes sense for us to take the log of it, because there's going to be n number of observations and the calculations becomes easier. We'll talk about, probably will not be able to talk about how, but we generally do log of likelihood. So how will this look like? If you have to take the log of this whole term, then it will be L1, right? And then you will say log of probability of t happening, my weight happening, given the all the n features, will be somewhere look like log of 1 by under root of 2 pi sigma, and exponential is there, so it will come down and it will look like minus 1 by, okay, let me, I don't think, okay, we have a space somehow, so but let me just write below. So this will be log of 1 upon under root of 2 pi sigma, and this will be minus 1 by 2 bracket tn minus wt xn, and this will, let's say, square divided by sigma square, right? So this is my this becomes my loss function here, and what I have to do is, for loss function I have to minimize this. So if basically I have to maximize this result, maximize this with respect to w. I want to maximize this L1, and to maximize this L1, what I have to do, if I want to maximize this, there are two terms, one is this term, one is this term, right? So if I have to maximize this result, what I need to do is I need to minimize this particular term, because because of this negativity. If I minimize this term, there will be minimum number subtracted from this value, and I will automatically have a maximum value. So what I basically need to do is I need to minimize only this particular term, which is tn minus wt xn whole square divided by 2 sigma square, right? So maximization of likelihood can be thought of as a minimization problem, wherein you just want to minimize this particular value because of the negative sign, right? So we are good. And in this particular term also, if you see, we are majorly concerned about this one, because sigma square will be a set value. You just need to worry about this particular term. You just need to work with this term. If you minimize this, then you will have your result, right? So we are good. This is what happens when we talk about the likelihood, that if we talk about a likelihood from a Gaussian distribution perspective, and likelihood is the major function which will come into the logistic regression. So there is a distribution for a linear regression. We took that as a distribution of a Gaussian, which is normal distribution. What is the probability of a given t given xn will be given by this particular rule, and this likelihood function is your loss function. What you need to do is you need to maximize for the likelihood. To maximize the likelihood, what we need to do is we need to minimize the second term, which is just this divided by the 2 divided by x square. Just give me 1 second. I need to have a glass of water. Okay, I think I picked up the time, which is just about 10:30. So what we'll do is after 10:30 we'll quickly cover, or maybe probably here itself we can, if you guys are okay, fine, I'll just quickly. In logistic regression you have a problem for 0 and 1, so that means it's a binary problem, and our binary distributions come from a Bernoulli's, right? It comes from a Bernoulli distribution, and Bernoulli distribution will look something like this, wherein you will say probability of Tn being equal to 0 will be 1 minus P, and the probability of Tn, basically right now we are not talking about the distribution, we'll talk about the distribution for the Bernoulli's as well, will be equal to P. Now we will associate this, whatever we have done previously for the regression, with this and try to do the same thing, wherein we talk about the log likelihood and all those things. But because probability values, we are talking about the probabilities values, which will be given in this particular case by sigmoid function for your Wxn. Log likelihood will give you any numbers, numbers which will not be between 0 and 1. So what you need to do is, for the probabilities, you need to use a sigmoid function and bring it in the value between 0 and 1. So what is this sigmoid function on geometry looks like? A sigmoid function which I mentioned, like sigma for a given a is written by 1 upon 1 plus exponential of minus a, right? So what this function technically does is that when you run a logistic regression, you actually do not get a value between 0 and 1, or you do not get actually 0 and 1 as a value. What you get is a log likelihood of that function. When you get a log likelihood of that function, you need to convert that into a probability, and then from that probability you convert that into a probability by using the sigmoid function, and that probability value lies between 0 and 1, and then you decide upon what should be my threshold or a cutoff. Above that cutoff of that probability, you will say it's going to be 1. Below that, you will say it's going to be 0. So if I have to draw, then this is how it will look like. But your values can result into minus infinity to infinity, and at a it will be 1 by 2, and it can maximum be 1. So you will have a curve like this. Okay, so what it does is it restricts your values between 0 and 1, or maps basically your values between 0 and 1. Okay, and the derivative for sigma, so we can probably do that as well. So so if I have to rewrite this thing which I have just mentioned above here, Tn, which will probably be written now as probability of Tn given Xn will be 1 minus sigma Wtxn, and then sigma Wtxn, and this will result into 0. This will give you 1s. So goal here is to identify the parameter W. So goal is to identify the Wt parameters. And how do you get this? You have to train your model, and you will get using the sigmoid function, you will convert those values into 0s and 1s, and you will make a prediction. So your prediction for yn will be made by using sigma of Wtxn, right? And then as I said, that you use a threshold, because this will be a probability term. You use a threshold and you convert them into divide them into zeros and values. Now this function which we have, so this function which we are talking about here, yes. Okay, I think again. Okay, so this function which we are talking about here, we need a loss function to estimate the parameters here, right? What we need is, again, we need to identify the W's. So again, we need to have a loss function. So we need the loss function. When we talk about the loss function, in our particular case, the this equation which we talk about can be written as, this particular equation can be written as probability of Tn given Xn is equal to 1 minus sigma of Wt xn, and this will be raised to the power 1 minus Tn multiplied by sigma of Wtxn raised to the power T of n. Okay. And what you need to do is you need to maximize this. So you take again, you will take, this is a probability, as I said, that because there's a multiplication, you will take into log of this, log likelihood. And when you take the log likelihood, you will end up with L1, which is going to be log of L, and which will be 1 minus, this will from the top, it will come then Tn, and this will be log of 1 minus sigma bracket Wtxn. And then this, because this was multiplication, it will get converted into plus because of the log, and you will have Tn, right? And then you will have log of sigma Wtxn, right? Now, we want to maximize this. How we can maximize this? We want to maximize this factor. So as I said, maximization problems are more of a concave problem. Minimization problems are easy to solve, which is convex. So what we do is we generally write a negative sign of this. So instead of saying max of L1, we will say max of L minus L1. So then this will become, you will have negative signs in front of this, minus 1 by Tn log of bracket 1 minus sigma Wtxn, then minus Tn log of sigma Wtxn, right? Now this particular function which you are seeing, this is the loss function. This one is the loss function for logistic regression. And in Python and every time when you will see, this function is specifically named as, this particular deal is specifically named as something called as binary entropy. Sorry, not just exactly entropy, it should be called as binary cross entropy. Okay, so you can select your, when you're learning a logistic regression, when you're doing gradient descent, you can say that I want my loss function, which I need to be optimized, is should be binary cross entropy function. And I think now you will understand when you see that what this exactly binary cross entropy function means like. And for the gradient descent, quickly another, probably we'll take a break here. I think we have already 5 minutes. We'll take a break here, and then probably come back and see when we say the, again, because we have to do the gradient descent here as well. When we do the gradient descent, the gradient of the sigmoid function is pretty known function, and it gets easier for us to just solve it quickly. So far so good. I hope that I have not bored you people to death, and some of you are not sleeping. First of all, we are not on the same room, so that's a challenge. So I'll just switch on my camera and stop sharing. Any questions you have so far? No. So Priya, I think Priyadashini, we can probably go for a break. For about.
Yes, Mohit, we will have a break for half an hour.
Yep, sure, we can do that.
Yeah, we'll be back at 11 o'clock.
Okay, sure. Thank you, everyone.
Participants, please fill in the attendance form. Yeah, go ahead, Mohit.
Yep, no, so let's meet after at 11 o'clock. Let's have a cup of coffee, and please feel free to tell me that Mohit, you are boring us. So then I can either feel good about it, or I can feel bad about it. If I feel bad about it, then I'm gonna bore you even more. If I feel good, then I'll see, okay, if I can reduce some of the mathematics and talk about some other interesting things. Yeah, but your feedback is important. Okay, guys.
Stop.
participants, the feedback link will be shared only at the end of all the 3 sessions. However, attendance filling is mandatory for each and every session. So we request you to kindly fill the attendance alone for this first session. It is posted by Dr. Priyadarshini in the chat box. Mohit, Mohitji, shall we start?
Yes, we can start.
Yes. Welcome back to the second session. I hope the participants are also eagerly awaiting this session. So over to you, Mohitji.
Okay, thank you. So let me just share my screen back again. Yeah. So we were talking about the same thing which we want to do is, let's choose a little bit higher number itself here. So what we want to do was, this is a gradient descent function. We know that there is going to be an error function. We want to optimize that weights for my parameters, and in here we have used a function which is called as sigmoid function. And the derivative of sigmoid function is basically, everybody almost always remembers it. If so sigmoid is 1 upon 1 plus e minus a, and the derivative turns out to be this one, ea bracket 1 minus sigmoid of a. Okay, sigma of a. So this is basically, you have your derivative here. Now why we are using sigmoid, the idea is very simple, and it's the only reason that your model, when you run a binary logistic regression model, it gets you a number between minus infinity and infinity, plus infinity. And what you want to do is, you want to convert that into a probability, so that you get the likelihood of an email being spam. To get to that number, you do a probability, and to get to the probability numbers, what you do is, you convert that any number between minus infinity to infinity to a range of 0 and 1 into probability numbers. And that one way of doing that is using sigmoid function. So sigmoid function is not the only function which can be used. There are other functions as well. And I do not know, sigmoid is very, very popular when it comes to logistic regression. And I have no, probably there is no particular reason why people use or decided to use with the sigmoid function. Doesn't look like that there is mathematical advantage or something like that. But that's why, but that's something which is very popular. But there are other family functions which belong to. So in this whole linear regression and logistic regression, the goal or the main idea which I wanted to bring up was that there is always going to be some input function which you will represent by x, which we will call it as input features or variables or column names. There's going to be a target value. There is going to be a function which we want to learn, which is going to be which will have certain parameters. Okay, and that function is, to learn those parameters we will need a cost function. Okay, and that cost function will help us get to the kind of identify the errors, and then those errors we need to minimize those errors. And how do we minimize those errors? By identifying the optimal weights. Okay, and the process of finding that optimal weights is through, one way of getting to the optimal weights is through gradient descent. That's what we have learned so far, and I specifically focus on gradient descent because almost every other deep learning algorithm survives, or gradient descent is an integral part of it. Without gradient descent, you will not hardly find any algorithm which will be working as part of deep learning. Okay, so we all are good and clear up till so far. If you have any questions, please feel free to shoot. And similarly, like when you build a logistic regression, we use likelihood because the problem is about zeros and ones. For continuous problem, it's not a problem, but you can also have for the continuous problems, you can have a likelihood of a number being present. Like I just mentioned, weight is a continuous word number. You can also have what is the likelihood of Mohit having a weight of 80 kgs, and we can solve that problem given the features. Okay, but generally log likelihoods or likelihoods are basically used with classification problems, wherein we are talking about what is the probability of having ones, what is the likelihood of having zero, and so on. So good, we are good. Okay, now let's look at what sort of problems we have basically talked about so far. We talked about one as linear regression. So in linear regression, you will have x variable, x features, and then you wanted to predict a y. Let's say you have x as your square feet, and y is as your probably price of the house, right? Price of a house is dependent upon the square feet. So you probably may have a data like this. As the square price increases, as the square feet increases, your price also increases. So you then end up having a a linear regression problem like this. Okay, it's a pretty good straightforward line. You can also have a problem wherein I mentioned about something called as spam, not spam, cancer, not cancer. A customer will buy a new credit card or not. That's called as whether he'll buy a credit card or not. That's called a propensity model. If he already has my company's card, will he buy the next level card or the higher product in the credit card range or not? That's your cross selling. That's your upselling. Then you have a cross selling method, whether he will, if he has a credit card, will he get a loan from my bank or not? So this is a cross selling. But in all these, this is like a binary. You can have other problems wherein you have more than one choices to make, but in this particular case you have either yes, or you are talking about no. So in when we are solving problems, we'll generally represent no's by 0 and yeses by 1s. In this particular case, you will always have values like this examples, and then you have your x features. X features can be anything, but what we try to do is we try to use this sigmoid function and try to get the values in this particular range, and then we decide on a cutoff, and we say any value greater than this will be considered as 1, any value less than this will be considered as 0. Now when you're doing a logistic regression and things like that, you can also decide that maybe this value most of the times people will take 0.50, but probably in your business scenario, and that's why business acumen is very important, that 0.50 is not a good idea to take. Why? For example, if I say that if I request one of you, can you lend me 2 lakhs rupees, and the probability of me returning that money to you is 50%, will will you guys give me money? If somebody asks me this question, I will certainly not give with 50% probability of somebody returning my money. Right? So that's not a good idea. If bank has to decide a thing whether they should give you a loan or not, and there is a cutoff of 0.5 threshold, and you say that okay, there is a probability, 50% probability that this person will return a loan, then no bank will give you a loan. So what we do is, certain cases, if you understand your business, you can raise your cutoff threshold value and you can move it to somewhere very even higher value. Maybe I'll move it to somewhere this close, because if it's about money, I think everybody's running, it's all about money. So we'll probably move it to this bit, maybe pro 0.75. I have to be 75% sure, or maybe 80%, or maybe 90%. But that's what I will technically try to do. I'll try to move the cutoff to a very high level wherein I have to be more certain that my money will come back, or the bank has to be more certain that the money will come back, and then only they will give you the money back. So CIBIL score is somewhere on the same ideas. That's why you do not have a CIBIL score of 500. They say that you have minimum have to have a 750 or 780. Then only you should be able to eligible for loan. And even after eligible for loan, there is some other parameters they look into to say that okay, whether you should get the loan or not. So what I basically say is, certain cases you may also want to reduce your probabilities. So there are many other things which we can do. It's not just you increase the probabilities. Certain cases you maybe want to decrease your probability. Now, sometimes, some cases you will not. Basically, why we are doing this higher cutoff and lower cutoff is for the cost of predicting wrong. Okay, cost. What is the cost involved if my prediction goes wrong? Right. So if the cost is very high, then I should be more certain the probability of event happening. If that is not the case, then it's a problem for me. So sometimes I do not know that cost. In business setup also, when I solved a couple of problems wherein I did not know about the cost function, in that case what we do is, there is a way to get to the optimal cutoff. There is a concept of true positives and true negatives. Will not talk too much about it. Okay, so what we are saying is this is going to be cut off. Let's say from 0 to 1, you can pick up any 0.1, 0.2, 0.3, so on up till 0.80, 0.90. These are your cutoffs. This is, let's say this is TPR, this is true positive rate, this is TNR, true negative rate. True positive rate means out of overall true positives, that is overall ones, how many you were able to predict. So how many you predicted correct positives, and TNR is out of total negatives which we have, how many you were able to predict correctly. And when you try to plot the graph, you will find at each cutoff you will have a different TPR and TNRs. So you will see that okay, TNR stands here, then TNR stands here, then TN stands here, then TNR stands here, then there, then here. And similarly for TPR, you will find that, okay, it was here, 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 it was here. So wherever these two numbers, these two lines, you know, kind of cross, maybe. So wherever these kind of cross each other, that becomes my optimal cutoff. And that's where I will say, okay, I will take probably this as 0.60 as my threshold, and here I will put that cut. Anything greater than that, I will say it's positive, and 3 greater than this. Now TPR and TNR generally you get from this confusion matrix, wherein which you can easily draw that confusion matrix. What you have in confusion matrix is 4 corners. So there is actuals, there is predicted. So you know, maybe we should make it predictions here, actuals here, actuals, and then predicted. So you have zeros and ones, you have zeros and ones. So A, B, C, D. So true positive rate is how many you predicted out of actual. So D by C plus D, D by C plus D. And true negatives is A upon A plus B. Okay, that's how. So at every cutoff, these numbers will change. Right now, this table, let's say probably it at 0. When you say 0, that means everything becomes positive. When you say 0.1, and some will be negative, most of them will be still negative, and so on. And you will have your, you know, different, every time you do this calculation, and you can draw this graph. Any questions? Okay, so from this matrix, there are a couple of things which are very important. One is called as precision. One is recall. There is something which we calculate. We call it as F1 score. F1 has other variants wherein F beta score you can call it. Okay, so and then you have simple stuffs like TPR, TNR. You have accuracy, overall accuracy of the model, which is nothing but A plus D by the total number of observations which we have. Total observations which we have, that's accuracy. If your data is imbalanced, when we say imbalance, what do we mean is generally we expect equal number of examples for both ones and zeros. Okay, so but in case your ones is, let's say you have ones as 70 and zeros is 30, this is still acceptable. But let's say this moves further 80-20, 90-10, 95-5, those are called as imbalanced numbers. If these are imbalanced, then instead of looking at the accuracy, what you should do is you should start looking into precision, recall, or F scores. Now precision is basically the simplest way to remember precision is that your denominator is your total predictions. Okay, let's say out of 100 total predictions you made for one is 80. In actuality, there were maybe out of 200, let's say 100 were 80 were actual, 80 you made as your you predicted as ones. Some of them can be misclassification, so it can be 0. But in actuality, there were 100 were ones. So what will happen? You will have 100 by 80. Okay, and so precision basically is saying that whatever number I am predicting as ones, how many out of those are actually ones? Okay, then you have recall. Recall is out of total numbers which I total ones, how many I'm actually able to recall as ones. F1 score is nothing but a harmonic mean between precision and recall. Okay, and there is beta score is there, wherein there's a beta formula involved, which instead here F1 beta value is 1, so that's a simple formula wherein you will have 1 by P plus 1 by R by 2, right? So this is how you calculate. So I think you will end up having some formula is beta is there, so you'll end up having, we can solve this, you will end up having a value. But if your beta is there, then you will have some value multiplied with here, that will be your beta. So that's how your beta scores are there. So beta actually helps you to put more either emphasis more on precision or recall. And if your beta is high, you'll be putting less emphasis on precision. If your beta is low, you'll be putting high value on the high importance to the precision. Now, what sort of problem we have? These both functions with these both things which we are saying, they both belong to the linear families. Okay, so if you see here also, There is kind of a line which you're drawing here. Also, there is a line, kind of a line you're drawing. So, but these still belong to a less complex data sets. Sometimes your data sets can be really, really complex, and a line may not be sufficient to separate your data. Okay, so what I mean by that? So let's say your data looks like this. And you bet there are data sets which will look like this. So we call it as a circle circle in circle data. So sometimes your data set may look like this. You may have an x variable here, you may x1 and x2. If you draw your data set looks like this. Now there does not seem to be any particular line which can be used to separate or get the good result. So you can draw a line like this, or you may probably try some line other than this. You can probably try a line like this, but you will always have a problem. Probably you will be able to do like this, but you are doing a lot of misclassifications here. So this does not seem to be a line which will separate this out. In this particular case, we are looking for a solution which can probably, if an algorithm can draw something like this, right, then we are able to separate out our examples. Now I'm just going to draw a little bit more um, uh, acceptable form of data, so that you understand that how why multi layers can help, or becomes nice to have, why people started talking about multi-layer things. Okay, so let's say we have probably data like this, and then probably maybe some values here as well. Let's say we have a data like this. Now in a data set, or maybe I'll make it even further simpler. By this should be good. Maybe something here. Now, if I have a data set like this, if somehow I can get to a line, okay, I can get to define a logistic regression which will separate the data set. Let's say if I build one logistic regression and I am able to develop a line like this. Okay, then I try to build the second logistic regression and I get a line like this, right? And then I try to build a third logistic regression and I get a line like this. Okay, now here what I have done is I have drawn multiple logistic regressions. So this was one logistic regression, this was second, this was third logistic regression. What I was able to do or achieve was that I was able to get with the linear setup, I was able to get a non-linear setup, right? So I was able to get this, and I was able to separate out. And this is the whole concept. This is the whole thing which neural networks helps us to achieve. And that's where, when the data gets complex, there arose a requirement for multiple layers rather than just talking about one single line. Okay, that's what your requirement came into the existence. Now if we have to talk about I think everybody should be aware of this. There is a toy example which we can talk about. You know about this function, like XOR function. What does XOR function says? That if you have 0 and 0, then it will be 0. If you have 0 and 1, then it will be 1. If you have 1 and 0, then it will be 1. If you have what is left, 1 and 1, then it will be 0. Right? Let's say that this is your data set, and you have, so you can imagine this into a table wherein you have 0 0 0 1 0 1 0 1 1 0 0 as 0. Okay, this is your XOR table. So this becomes my y, this becomes the x1 and x2. This is what I want to solve, and you can solve this using a linear regression or a logistic regression. But let's look at if I solve this problem by linear regression. So if you remember what was the formula which we have used, there are 4 observations. So my error function will become 1 by 4, and if I do this, then it will be n is equal to 1 to 4, and I know that this is the true value minus weight of weight transpose multiplied by xn, right? And then we square this value, right? So xn, we know that here everything is a vector. W is also vector, x is also a vector. Here in this case, x has only 2 values, 0 and 0, 1 and 0, 0 and 1 and 0, 0. So your xn basically will look in programming, it will look something like this, wherein you will have 2 values. Okay, so if you solve this for the W, then obviously we can solve this, but let's not waste the time in solving this particular one. But if you solve this for the W, you will find that the W will end up having a vector, and you need to understand that there is going to be one bias term as well, right? So you will end up having values 0.5 and then 0 0, wherein 0.5 will be your bias, and then your this was your weight 1, this will be under your weight 2. Okay, so what we are saying here is that yn becomes wt of xn, and it is always going to be 0.5. So you see, we are not learning anything. What this is going to be always case. So what happens is that if we have something like this, this indicates that you are technically learning nothing at it. And so the question is, how do I fix this issue? How do I fix this particular problem? Because I'm not going to learn anything if I'm going to go by traditional linear regressions or logistic regressions, wherein the loss function is MSE. In this particular case, we picked up MSE. You can pick any other loss functions. We generally, when we're talking about gradients, we do not pick up MAE because that's a constant number, and you do not get gradients is not possible there. So how do we fix this particular problem is through the introduction of this linear function, which I through this multi-layer layers which we just talked about, which in particular specifically called as hidden layer in deep learning. Okay, so far what we have done is we said that we have x1 and we had x2, and using these two we were predicting y, right? And now what I'm saying is we should have an x1, we will have an x2, and rather than directly getting to y, what we're gonna do is we're gonna create intermediate variables a1 and a2, and once we create this through these a1 variables, we're gonna get their activations. We will call this as probably z1 and z2, and this basically activation is a function, and this function is a non-linear function. Please take a note of this, because this is very important. If you understand this, I think you will have a very strong foundation for your neural networks. So this is going to be a non-linear function, and this is a linear one. Okay, and then finally what you do is you use these activated non-linear functions to predict your y. And this whole setup, this one is called as hidden layer. Okay, so as I mentioned, let's just write it also down here for you if you guys are taking notes, that a1 and your a2 were linear functions, which is basically a number resulting because of linear combination of functions. And as I said, that z1 and z2 are your non-linear functions. And I am again repeating this. Please take notes, because once I go to the notebook, you will see all these things happening, and it will be really interesting to see that how things get really solved. Okay, so when you do this, so the question again, what does linear part doing? Okay, linear part is basically capturing the interactions. If you see x1 and x2, generally in your linear regression, when you're solving a linear regression or typical machine learning algorithms, what you have to do is you have to define your features, you have to create new features, you have to think about the business, and then you have to create interactive features. For example, you can have a feature in, you're doing a linear regression and you want to predict the salary of a person. There is a variable which is about education, and then there is a variable which is number of years of experience. Individually these two variables contribute to the salary, but there is also an interaction between these two variables. A person being a PhD and having a experience of 10 years will definitely be earning something very high. A person who is graduate and is have a 10 years of experience will definitely be earning little less. So individually these variables have an impact on the salary, but they also have an interaction and they have an impact on the your target variable. So in neural networks, what happens is that this you are able to capture automatically, okay, through this linear combination. That's why you will find saying that you don't really have to worry about the feature selection, or you don't really have to worry about how to create new features. But that is also, in my opinion, my experience, when you come to the real world, that's also primarily partially true, because 80-90% is true. But if you have a business knowledge, it still really helps you to build a better neural networks or better solutions for, or better, when I say solution, I'm only talking from the data science algorithmics perspective. It gives you much better opportunity to develop a better solution. Okay, so this is what is a structure for the deep learning. So deep learning structure is linearity is followed by non-linearity. Okay, so that is what the very basic structure for deep learning is. So deep learning structure is that linearity is followed by non-linearity. And then you can just keep adding as many layers that you want, but let's keep it at this level. So this is what you do. So if you technically see, what you have done is you have added a linear regression. This is your first logistic regression. It ends up exactly like a logistic regression. This also ends up like a logistic regression. You get a y, but if you want this y to be a binary, you can add a sigmoid function before that, and you can convert this into a maybe a2 you can add, and you can convert this, because this is going to be a number, so you can convert this into a ones and zeros, or you can have a cross validation function and all those things, cross entropy functions. Okay, so f is linear and the whole network becomes linear, which will correspond to what is solved. Yeah, just sorry, before I make this statement, what I want to say is that if the non-linearity part is not available here, okay, if you do not have a non-linearity part, then this algorithm is nothing but an algorithm wherein you will still end up having the same result like this particular network, wherein you will end up with 0.5 if you solve it. Okay, just give me a second. Okay, this bit is clear. Any questions on this particular part? Okay, so in this non-linearity function, traditionally people were using sigmoid, softmax, and things like that. But one function which is a non-linear function which is very famous is this ReLU function, which is called as, in modern, I would rather say this word, modern neural networks, this ReLU function, which is called as rectified linear unit. Okay, rectified linear unit is the function which is very nonlinear function, which is very popular, and it happens to give a very good results. Now if you have a question that why ReLU and why not sigmoid, then I do not have any answers. It just happened, and there is no mathematical, again, particular thing that why ReLU is performing well. They just happen to happen that ReLU function, nonlinear functions perform really well into the data. So this function can be written as f of a. What this does is it tries to pick up the maximum value between a and 0. Okay, and if I have to draw this, then what we are saying is that This is amazing. I have right. This is the best I could do for the straight line. Okay, so yeah, so you have a here. This is a function of a. Any value above 0, it will give you some positive results, but for the values which are less than 0, you will end up having a 0 value. So it will be like, you will end up having a 0 value. This, otherwise you will have a 1. Okay, right. Now now when we use this ReLU function in here, when we were trying to solve this toy example, basically I'm sorry, I just forgot in between. So when you are trying to solve this problem, if we go by this, as I said, that you will always end up with 0.5. But to solve this problem, if you use this, so here you further, if I say linear, means you will have a W1 X1. Here you will have W2 X2. Okay, and then this will, we should write W1 1, and this will be W21 X2, and this will be W12 A2, and this will be W3 A2. Okay, like this. So this is a linear thing, and then you have an activation function wherein we're going to use this ReLU function, and then you get the results. So what we have found is that if you use ReLU, you get weights which will fall into this category. So your W1, which is probably a bias, ends up having 0 1 1, and your W2 for the 1 ends up having -1 1 1, and then you have W for the second weight, which is your after the activation function, when you combine, which was drawing here, which you get tends to be 0 1 -2. Okay, and with these weights you will see that you get exact output. When I say exact output, what I mean is that you get exactly these output. For 0 0 you get 0, for 1 0 you get 1, for 0 1 you get 1, for 0 0 you get 1. Okay, now there is, obviously we can solve this by hand as well, or by using a programming language, but let's just avoid that. You will exactly get these words, and you will be able to get the exact output if you use this FA. So why I told you this is that the goal was to help you understand that the neural network with this hidden layer and the ReLU as a function has the capacity to learn the parameters that would result into desired output. Okay, how we achieve it, how we optimize it is not the goal. I just wanted to showcase you or tell you that if you use this kind of a structure, for a very simple problem, which is a XOR problem, you will find that you are able to achieve the exact output. Okay, so this hidden units are very interesting. Okay, these A1 and A2 are called as hidden units. So these hidden units are very exciting, and that's why I first activation function from the non-linearity perspective is the ReLU, which we have discussed so far, and it has got some maybe some points which will be positives for us, some negatives for us. One such negative point, if you see, is this is 0, right? If your data has exactly half number inputs which you are following, x1 is x2, the 50% of it is inputs are zeros, then what will happen that your outputs for basically I should say output for zeros, or maybe we can probably state it like that you will get output as 0 for half the domain. Okay, when I say domain, you can probably think of this line, this exactly half of this you will find zeros, or you can think of a sparse data. I hope you understand what is a sparse data. So sparse variable, if you talk about only x variable, x1 variable, then it's called as a sparse if there are a lot of zeros as part of the text variable. Okay, and especially with image classification and all, you will find lot of zeros happening. And when I'll go to the example, I'll help you understand that why there tends to be lot of zeros and the data tends to be very sparse. Okay, especially if you're using the grayscale. So in this particular case, you will only have derivatives for wherein derivative is 1, right? Derivative is 1 when the output unit is output is non-zero. But with this function, what happens is the gradient is easier to compute. Okay, ReLU makes gradient easier to compute. Gradient is easier to compute when you're obviously for zeros, you really don't have to do anything. You will not have any gradients when output is non-zero. Okay, and so computation becomes easier. It also makes learning easier. Learning gets easier. And this is also anti-semantic. Semantic. Anti-semantic response, basically what does this mean is it will only give you values as 1 whenever it is needed. Okay, so something of you must have heard neural networks behavior like your brain, wherein actually this is concept has come from there itself. So when you touch a current, there is specific neurons which gets that information and they open the gate to take it to particular neuron. So ones and zeros kind of way it happens. Wherever the signal is not required, it will probably not send that shocking information to your brain. Okay, you probably, if you're eating a bland food or if you're eating every day the same thing, you do not see any excitements. That's what probably it's not happening. But if you're in childhood, if you have touched a live wire, then today also you are scared because you know that feeling how it is going to be. So that signal automatically gets and opens the neuron whenever it is required. But this does not happen every now and then for your brain that you're scared of touching power lines or anything else. But if you see that the wire is open and the task can result into you getting a shock, then your neurons opens a gate and you get a 1 as a signal. So similarly happens in this particular case. We are saying that this response is anti-semantic. Whenever it is required, you get the 1s, else you will not get the 1. But again, if your data set is very sparse, then probably ReLU may not be a better idea. There are certain types of issues also related with that, but so far it is one of the best. So dealing with this problem wherein we are talking about the zeros. So now what we have done is now we have moved in types. Certainly, if you see the journey has been, we talked about linear regression, we talked about logistic regression, then we slowly slipped into neural networks. And then within neural networks, we are talking about the activation functions, which are non-linear activation functions, because those are the most important part of your neural networks. Okay, without non-linearity functions, neural networks are nothing. Okay, so ReLU is one such new function, and we know that ReLU had some issues. So there is something, there are other generalizations which we have. One such generalization is called as leaky ReLU. Okay, so leaky ReLU helps you deal with zeros. It helps you deal with zeros. So in this particular case, what happens is that you know that this is, we just mentioned max of a comma 0, right? In addition to this, we will have a fixed parameter alpha. You can say alpha I, and we will multiply it with the minimum of 0 and a. Okay, this alpha is fixed, so you can, you can, when you're writing a code, you can give that for a ReLU, you can give that value. But what will happen if you look at the graph is, you have this graph. Earlier it was supposed to be particularly, from here it was supposed to be like this, and here it was supposed to be like this. But now because of the leaky ReLU, because of this alpha which we are adding small value, what will happen, you will have a slightly below this line like this. So you don't end up with 0, but you end up with some negative values, and that's how you so this is your leaky ReLU. So far good? Okay, I want everyone to say yes, good, and then we'll move forward. Okay. Doesn't look like it's good. Okay. So then the next thing is the other functions which we have already one of the functions we have already talked about is it's not just the leaky ReLU or ReLU. There are many other functions, which we have. One such set of group was functions was we had sigmoid function. I already told you we had sigmoid function. We also have hyperbolic tangent functions. Right, the idea again, all of these functions, they just bring up the non-linearity. So how they bring up the non-linearity, I think ReLU we already learned, sigmoid we already saw, but let me just draw once again. So you have this, it will have, let's say, something like this, and then you will end up having an S curve. Basically it's famous for its S curve, something like this it will happen, but this part will be not so low. If this will be exactly half basically. So this will be 1/2. This will be sigma of A, right? And here you will have the A value minus infinity to plus infinity, and the formula wise it is given by 1/1 plus exponential of minus A. Okay. Similarly, we have tangent 1. In tangent, what we have is the second part, tangent H function people call it. So you write it as tan H of A. And why we are writing A? Because of this particular activation function, okay, linearity. So in notebooks also, I think you will find this like this A. Okay, so that's why I'm writing A. But if it is can be W, basically this is WT and X. So this is going to be 2 sigma bracket 2A minus 1. Okay, and then this can be reopened and look like something like this: e raised to the power minus 2A upon 1 plus e raised to the power minus 2A. Okay, so this is your tangent hyperbolic function. What it does is it restricts the value between -1 and +1. So you will end up having, let's say this is 1, this is -1, then you will end up having something like this. So both functions, basically this sigmoid function and your sigmoid functions, they both tend to um, kind of saturate, right, at the end of the domains. So it will saturate at 1 and -1. The sigmoid function will saturate between this 0 and 1. So they kind of saturate things between these limits. Okay. So saturation here means the derivatives, I mean mathematically what saturation is representing here is that derivatives are close to 0 and very, very small. So far we are good. So these are some of the famous, there are other functions as well, other activation functions as well, but these are some of the very, very famous. ReLU is, I think, one of the most used functions. If there are others, I have probably used them, but I do not really remember their function names and things like that. And to be honest, it's not necessary to know them. I also, when I started my career, it's not that from the very first day I knew about all those things. With time, initially I was a consumer, then I slowly became more aggressive, then started implementing papers, and that's where I started remembering these kind of things and understanding what exactly happens. Now in this kind of a setup, right, how do we, the question still is, we want to have a optimal number of weights. We still need to solve that problem of getting the my cost function is there and I want to get to the optimal number of W's. So I still need to identify how to get my parameter W as one of the best parameters. And in neural networks, in this hidden layer kind of a setup, right now what I showed you is just a one directional. This is also called as feed forward networks, because we started from x1 x2, we got a2 a1, and then a1 a2 we activated, then from there we activated non-linear functions, and then we got dy. This is called as feed forward network. Feed forward, this is only in one direction. So here you see whatever W you have initialized, that's what you will keep with, and you will get in one direction and you will get to y. But it's a good idea if somehow I can look into this value and then walk back and correct my path for the W's, then it will be really fantastic. And that is your actual deep neural network or neural networks, wherein you are not just looking in forward direction, you are able to walk backwards and correct and rework, because each one of them is bringing some error. So you had y, you gonna have a y hat, you compare this, you see an error. Your goal is to have as low error as possible. And how one way to do that is exactly like you study, right? You go to an exam hall, you give the papers first, you prepare for your examination, then you go to your exam, you give your exam, you get the numbers, and then if you're not shocked, if you are out of 100 you got 90, 85, 99, then you're happy. But if you're shocked, you see that you have got results at 60 or 70 or 50, which is not matching to what you prepared, then what you do is you take that new paper back and you compare with your solutions with what you have done, and then you realize, okay, that most of this error or most of the marks I lost in this particular question. And similarly, I'm going to do this algorithm can do the same thing through looking back, going through this path again backwards, and trying to understand that which weights are actually, or which weights are basically responsible for your x variable, which of them I need to tweak or optimize or decrease or increase their contribution to understand how I can reduce this error. And this process of doing this is called, we do this through back propagation. Okay. And to understand the back propagation from mathematics, you have to just pick one rule. If you understand, so we now move into back propagation. Okay. So to understand the back propagation, we first need to understand the chain rule. Chain rule of calculus. Okay. In chain rule of calculus, let's first take the scalar example. It will not be very difficult for the other one. If we take the scalar case, let's say we have a z, which is nothing but a function of x, and we have y, which is nothing but a function of z. Okay. So what we are saying here is, or I have written both with f, we can probably use g notation here. Function of g, right? So what we are saying that you have an input, you pass it into a z, you use that function, and then you get an output y. Okay. So suppose what we are saying, you have an input x and you apply a function on it to get the z, and then you apply this another function on z to get the y. Okay. So what we are happening is, this is happening, cascading is happening, a cascading of function is happening. So if I have to take the derivative of y with respect to x, because y is responsible for my error, kind of. So not kind of, it is actually. So if I have to say what is the d of y with respect to x, then I use a chain rule. First what I need to do is I need to get the d of y with respect to d of z, and then I multiply it with d of z with respect to d of x. Okay. And if it is, this is for this scalar case, right? Now if this is not a scalar case, if this is a vector case, then what I do is I simply, I mean the same thing in the vector case, probably my z will, x will basically, s will be what? S will be a real numbers, right? Of m dimension. Then you will have z will also, because x is in m direction, then z will also be some n dimensions. And then you have y, and y will be what? Y will also be a real number, but it will be just, one, it will not have n dimensions. If you're talking about just one value, right? At a time, you will predict, given n number of features, n number of activations, you are just going to give the one value for it. I hope this bit is clear. This understanding is very important. So what I am saying is, you have square feet, you have number of balconies, you have number of bedrooms, and then you have locality, and then you are predicting the price of the house. So this is x1. So you have n number of features, m number of features. You do the activations, you get n number of z's, and there is only just one price which you're talking about. So that's why y is just one real number. There is no dimension to it. Okay, so in the vector case, what you are just going to do is you will so your z again is a function of x, and your y is again a function of g, function of z. Right, and if you are predicting, then what you when you want to do in this particular case, how I will write, I will say d of y given d of xi, because now there are x number of observations and all those things happening here. So then this will be nothing but a submission of you will be have n from I to 1, and you will have derivative of y given derivative of z zi, and then you will have derivative of zi given derivative of xi. So to calculate the gradients and to get to that step information, that where should I move, if I have to draw this put into the picture, what I'm saying is you have an xi, and you had obviously there was a1 a2 a3, but we are just writing z1 z2 z3 here, and then you got the y value. Now we walk backward in this direction to understand which weights we can tweak to get which is responsible for getting the higher errors, or which weights are responsible for reducing the errors. This is the whole concept for back propagation. Okay, so chain rule, basically chain rule is chain rule is the main part of a back propagation. So we can also solve, if you want, we can solve quickly one thing with the back propagation, or I'll just give you an idea. Probably we don't really have to solve it, because everybody understands the chain rule. If you understand this, then we can move. I can probably skip that whole derivation thing of it, or probably we can do the half bit of it. So in neural networks, if you want to write this statement, in neural networks, gradient descent is achieved through back propagation. Okay, and you all know that why we are doing the gradient descent. We are doing the gradient descent to have optimal parameters. In this case, parameters are my weights. Okay, so how do we do that? To do that, I mean, to do the gradient descent, how do we do that gradient descent with respect to neural networks? So you have an error, let's say en, and you want to calculate the gradient with respect to all the weights. So what you have an error, you want to calculate the gradient with respect to all weights. Okay, how we'll write this, we will say I have an error and I want to calculate it with respect to all the weights. So all weights can be represented by ij, and this is for the n dimensions in the neural network. This is what I want to calculate. Now let's look at a maybe what do you say, let's draw a small network. Even the small network will look very cumbersome, but let's give our best shot. So this is your input features, x1 x2, and then let's say you have only one hidden layer with 3 nodes. So this is a1 for the first one, this is a2 for the first one, and a3 for the first one. Any point of time you do not understand any notation, please do let me know. Maybe I'll choose a different color for this one. Then we have this, this, right? And because you have A's, so you need to have activation functions. What we'll do is we'll just write on top of this one. We'll say Z11, and Z11 is a function of A11, right? actually we don't have to write A11, but we can probably this A1 basically. So I can remove this bit. And then you will have Z2 for the first one. Actually here also I should make a change on the, okay. And then here also Z3 for the first dimension, right? And then what you do is you're gonna have, let's pick up back the green color. So you combine them together, you get to a final A2 activation function, which will have its own Z, and then this will result into your Y output. So we can then give all these inputs to this one and pick another orange color and say that this will be so this is your sorry, this is my A1 for second dimension, right? And actually one we don't need the notation for one, to be honest, but that's fine. And that's you will have Z Z1 for second layer, second output value basically. And we know that these are all the non-linearities. So far good. I know I've taken quite a time if you to do this, but I'll be happy if you take something for remembrance that how this is all calculated. Okay, and the obviously the error here is going to be because if this is a binary problem, we have already saw that for binary problems your errors are calculated with this cross entropy, which was log of y, binary cross entropy. And there is also an entropy function, guys, which is in the machine learning algorithms for you will come across in random forest. This is different than the other one. Okay, so let's not confuse that. This is cross entropy. What shall we do? Yes, so then it's 1 minus t, and this is going to be log of bracket 1 minus y. So this is your error function. With respect to this, you have to calculate your gradient descent. So we'll do what we'll do is this part is a little bit more complex. So here also I will just write it down because this is going to be your y11 for 1. This is then probably just write down here y31 for your first. Okay, so this is another one. You can say y12, y13, then y21, y22, w22, then w23. Okay, these are going to be your weights. And eventually what is happening, if you want I will write it down. So your a1 here for 1 is basically w11 transpose x1. Okay, and then this actually we don't have to write down the transpose here because this is just right now a single value, say let's not make it complex. And a2 for first dimension will be w12 x2 and so on. Okay, yep. Sorry, basically sorry, there is not just one, right? There is other parameters also getting added here. So what I'll do is instead of writing here, I'll just write for 1 and you should be able to get it for the rest. So a1 for the first one is nothing but w11 x1 plus w12 x2 plus w13 x3 plus there is going to be this, bias weight. One bias weight is also there always. So that maybe probably is represented by like this. So this will also go there. Yes, somebody has a question. Okay, no, this is about the attendance only. Okay, so everybody is good. So similarly, you can see what your A2 will be and so on. So you can see that this is just a linear combination. This is nothing but your linear regression, right? Or then you add the activation to convert into a nonlinear function. So now En is happening at this end, and this is the function which we use. So your very first step to calculate the gradient ends up having like this. So you say gradient E1 with respect to A. Okay, basically A2. Now A2 is nothing but your y value. So we are not writing a y here. We are writing A2 here, and this will be given with respect to, and this can be let's just take the total error. Let's not make it n and all. So we'll say sigma of E divided by sigma of Z2. Sigma of Z2 has come from sigma of A2. Okay, so if you look at this, so we're talking about this, we want to calculate the n, and n error has come because of this Z1 and then with A1. So first I want to calculate what is the error which is contributed by just this second activation function to the Y. So when I say E of A2, this is what I want to calculate with respect to this, but we know that this is a chain rule which we have to apply. A2 has, first error has come because of A2 se pehle what we are doing is Z1. So we have to calculate the end error with Z1. And then this we have to multiply it with the Z2, which is coming because of A1. So that's why Z2, which is coming because of A2. This bit is clear. I really want you to help me understand or say out loud that yes, you understand this. Because we're going to keep doing this for the rest of the things. Yes, make me happy just for once. Okay, and then the second step would be, then you have to calculate the E weight with respect to the EW11. Now EW11 will be nothing but with respect to E with respect to your A2, and then this A2 is responsible and is coming from A2 with respect to first set of weights, right? So this, you know that you are calculating from this one. So you already know this one. This again will be calculated. In this particular case, A2, you know what is A2, like we know the A1 here. A2 also we know this is going to be W11 and so on. So we know this value, we can take the derivative with respect to W, and same in this fashion, what we keep doing is we keep moving in this direction and calculating, and at the end we just sum them together, we get the final gradient. And then we use that particular formula, which is which we just mentioned, right? That W tau plus 1 is equal to W W tau minus some learning rate and gradient of with respect to error. We can actually solve this whole thing, but I don't see any point here. But the idea is that you understand what is happening in the back propagation. In back propagation, we are trying to get to the error. We're trying to move into this direction. Once we move into this direction, we see where we get the most error. We first see, whether we are on this slope, whether we are which side we should move. And then once we understand this, we take our learning rate, which is a fixed quantity, this particular bit, and we multiplied by with this, we subtract it from the weight, and we move that much into this direction, in some direction. So we are moving in this direction, getting a gradient, partial derivation of with respect to this, then partial derivative with this, with respect to this, with respect to this. We sum them together. Here again, we get the partial derivative because of this, then partial derivative of this, partial derivative of this. This bit is actually easier. This one is little more complex, but you don't have to worry about it because it's computer who is going to do it. But the whole idea is the chain rule is being applied, and using a chain rule for vectors, we are solving this problem and we are able to get to the weights. Okay, any questions? So ultimately, if you look at the this part in computers, if you open, when you have run the back propagation, if you look at the weights, this will be a big matrix which will have a derivative with respect to each weight, basically up till W n n. Let's write this. So it will be a huge matrix which you will get for for how much each weight is contributing, and then you will update each of these weights. In our particular case, let's look at how many weights we are talking about. This matrix will be how big. So we'll have 1 2 3 4 5 6 7 8 9, and then 1 9 plus 3, 9 plus 3 would be 12, and 12 plus another 3, Bayes terms. So we'll have 15, around 15 weight parameters. Okay, and right now it's a very simple one single layer neural network, and we already have 15 parameters with only two inputs. With only two inputs, we have 15 parameters. If you increase one more variable, it will be again humongous. If you would have come across model names like BERT has, in the same structure, BERT has about 109 million parameters. 109 million, and this is based BERT uncased. There is also something called as BERT large, which has got about, I think, 340 million parameters. Okay, so neural networks can be, modern neural networks can be really aggressive. Okay, then we have VGG 19, VGG 16. Those got 19 million parameters, 16 million parameters, 10 million parameters, like that. Good, so far good. Okay, Priyadarshini, when we want to have a next break, just let me know. 12:30 around, right? 12:30, right? Okay, am I audible?
No, Mohit, we lost you. Now you're audible.
Okay, so I was asking, when do we have this break? But since when did you guys lost me?
Yeah, no, actually just now.
Okay.
We can break for 1 hour. So once the session, once you're done with the session, we can break for 1 hour.
Okay, great. So what I'll do is I'll just end up with one more thing here, and then probably we'll break for the lunch.
Sure.
So let's talk about neural networks. And in neural network, what you saw was you had an X variable and you had an X1 and X2, XD2, the D dimension. And then these are like traditional neural networks, what we used to do in the traditional neural network basically. And then you passed into a network, or you can say simple neural network, and you used to get a Y value. Okay, and generally this used to be 2 and 3 layers. And what does this means is that you will have a, for example, let's say earlier when we used to do feature selection or maybe a image classification, there used to be it's not something which is absolute. There are techniques from which we are not just passing the whole image, we extract some information from those images and then we pass them into the simple neural network. So these images, there's a technique based upon I'm forgetting the name. There's a technique based on histograms wherein you will identify the lines and the circles and all those things, and then those will become your features, and those features you will send inside this simple neural network, which will be which will have 2 or 3 hidden layers, and you will get your output. So what in previous neural networks we used to do is that the features were handcrafted. Okay, and in today's world, when we talk about deep learning is just going one step ahead of the neural network, wherein you have an X, you pass them into a deep neural network, and you get your Y. And when I say deep neural networks, what we are saying is many layers are present here. 200, 300, sometimes even more. Okay, so that much layers we are talking about. And there are many more complexities come into the picture. So to train deep neural networks, you need more data. It is able to do more. It requires more computational power, and you are able to build better models if you are able to have the domain specific knowledge. Like I already gave that example of translating, capturing a photo of the French words and then seeing that converted into your English or Hindi or Tamil or Telugu, all these things we can do in today's world. But if the font you have trained on is not the same font which is used on their billboards or in their books, then you will not be able to do that. So you need to understand that different fonts means a different thing when you talk about a computer, of how the computer looks at it, how the pixels work around with it. Okay, so there are few comments which probably is worth noting. And I think the first thing is when model is okay, we can probably stop here, take a break, and then come back, and then we will talk about things like uh, when these models do not perform well, how do we ensure that they perform well? So things will come like L2 regularization. First question is, when do we say the model is not performing well? What could be the probable reasons for that? We'll discuss about that. Then how do we fix them? Then your regularizations, your things like early stopping, dropouts, and then how do we optimize? Then within optimizations, the concept like momentum, and within after that, grad, and atom will come into picture. Then finally, we will close the today's talk. So far, if you have any questions, please do let me know. And if you like the session so far, please raise a thumbs up so that I can go and happily have my lunch. I'll stop sharing for now. Okay, so session has not been that great so far.
Participants, please encourage Mohit. He's giving so many interesting things.
Okay,
Please
don't worry. It can be overwhelming. It's okay, fine. But I hope that even if you are able to take care, take home or keep things like 40% of it, when you next time go through the same stuff, it should make much more sense. But yeah, there's something which we cannot ignore, so we have to go through them and we have to talk about it. Let's connect after the lunch, and then we will probably, now I'll see that I'll talk less about mathematics and more about the implementations and why we use and what we use, so that we can have a little bit more energy to you guys. Okay, let's connect after 1 hour. That's about maybe probably 40 minutes. Let's connect at 1 o'clock.
Yeah, sure. We will we'll be back at 1 o'clock.
Yeah. Okay. Thank you, everyone. Let's connect after lunch.
Thank you.
ஆமா சார் வேற 12 கிளாஸ் அவர்
Yeah, hello Priyadarshini. I hope everyone is back.
Mohit, shall we start?
Yes, we can start.
Welcome back to the third session of this data science workshop. We request all the participants to be interactive so that we can share knowledge among ourselves. Mohit, over to you.
Okay, thank you so much. So let's start with now we are into the foray of deep learning, right? So what with the deep learning, like every other model, when we build the model, there are three things which we basically three data sets we particularly make. One data set we make is the training data set. The other one is we sometimes called as dev, or popularly is called as validation set, and then you have a test data set. The test data set, the idea is that you should not see, and this is the future data set which you will have, you probably will not have a y, and you will only predict the y hat for this particular data set. But just to test the accuracy, we know that there is y, but we do not, so we still ensure that we do not, our algorithm do not see this data at all, and is only used for preparation or the final prediction that how my model has been performing. In the training data set, all these things which we said, there are features, all these data sets have features. We have a feature, we decide on the loss function, we want to optimize the parameters, we do all those things in this. And some algorithms, they may have a hyper parameters which we want to tune, and for that we will use the validation set to tune those parameters. And then once we have tuned, once we have selected that equation, that model is basically a mathematical equation. Once we have that equation, or in deep neural networks, it's the particularly collection of weights. Once we have those, we use the test data set, we pass those, that network, and into that, and you get the test results. Now if you have sometimes what happens that your training uh, may not perform well. Okay, so when model does not perform well, so what does not perform well look like? So let's say you have a training accuracy of 0.70. In development you are getting 0.68. However, in test you are only getting 0.20, or maybe less, or maybe little bit more, but it's not near to this number. Then this is a problem. Okay, now this can happen for multiple reasons. In fact, in the training also, you sometimes see that you are not getting better accuracy, so you are stuck at 0.30, 0.5, or your model is not seeing, or the performance of your model is not good, or a neural network or algorithm is not good on the training data set. That's what will fall into model does not perform well. Now there could be some set of reasons for which this could be happening. And in this particular scenario, we are talking about, when I say model not performing well, I am particularly talking about testing performance being poor. Model performance in test data set being very poor. Okay, so there could be multiple reasons for the model not performing well in the test data set. One such thing is first thing, when you see something like this happening, the first thing you should do is, or our first thing as a data scientist we do is, we verify if training is successful. Okay, now what do we mean by training is successful is that probably when I'm training my model, it's not successful. And what does this necessarily mean is that my loss the error which I'm seeing, or the loss function which I'm seeing, is not decreasing much. So my loss is not decreasing much. At least at the beginning, when we start the epochs and all, I expect my loss to decrease faster and then probably slowly. But if that is not happening, then there is a looks like that my training is not successful. And there could be a couple of reasons for my training not being successful or loss not decreasing. One of the major reasons is associated with coding issues. You may have your code, or while coding, you may have not implemented your loss function properly. When you are connecting the layers, you missed upon connecting the layers properly. Things like that can happen. So that's related to coding issue. Second is the architecture which you are using is not the neural network architecture. There are a lot of neural network architectures, but probably the architecture which you are using is not suitable. So this is could be related to architecture. So you need to ensure that you're using a well-suited architecture which suits your problem. And then third thing could be maybe related to optimization. That your optimization was not successful. Okay, so if your training is not successful, these are the things which we can check. Then if your training is successful, but still the testing performance is still poor. Okay, if that is the case, then one of the reasons for this happening could be the distribution. Okay, that your distribution of data in training or in test is very different as compared to um, training. Okay, for example, let's say your data, you were training a linear regression model and your data points were like this, and you fitted a line which falls like this. But if in the test, in the training, in the test data set, your data points are somewhere like this. Okay, so in this case, your model will never learn. You will never be able to have a better testing results. Okay, the other reason for your model not performing well is something called as overfitting.
Excuse me, Mohit.
Yes.
Have you shared the screen?
Oh, sorry, I'm not shared the screen. Is it? Okay. My bad. Okay. Yes.
Okay.
So let's just
Okay.
quickly watch through. Yes. Okay. My bad.
Okay.
Okay. So we have this training, development, validation. So we, as I mentioned, that in training your accuracy is 0.6, in your validation 0.68, and test your 0.20. That means your model is not performing well. And if this is the case, then this particular case wherein you have 0.7 and 0.20, this is called an O of it. But whenever we build a model, we have to decide that why my model is not performing well. So that's the first question. And validation is something which we use for hyperparameter tuning only. Okay, or if your algorithm does not have an hyperparameter, then it can be used as a second testing deal, wherein you build the training model, or you are doing a cross validation, then you can use a validation set to see the results. So that's where we use it. So the first thing was to verify if my training is successful or not. If my model is not performing well, the first thing I check is, as a data scientist, you should check whether your training has been successful or not. And by saying training is successful or not, what we mean is whether the loss is decreasing much or not. So that means your loss is not decreasing much, and it's probably stagnant, or it's very slowly moving. So this kind of issue could be resulted of three things. One is coding issue, wherein you probably fail to code properly your loss function. You fail to code the layers together. This can also result into errors as sometimes, things like that. And then architectures, deep neural network, I said that a lot of architectures are there, but if you are not using the correct architecture, you can have a problem. Your training will not be successful. And then optimization could be another reason that the optimization is not happening the way you should. Figure out the optimal point using the gradient descent or different functions, that is not happening properly. The other thing is that if training is successful, there could be still chances the testing performance is poor. In that case, what you do is that testing could be one of the reasons for that happening could be the distribution of data in test could be very different than the distribution in the training set. So let's say I train my data on this particular set and I got a regression line here, but my testing data is something like this. So this way you will never be able to identify. Okay. And then there is this term which I said, overfitting. Overfitting means sometimes what happens is to see what we want to do is we want to, let's say again, this is how my data looks like. And if I am building a model, then a linear regression model, so my line would look something like this, which is a pretty decent good line. And in test, you will have your data points, somewhere of these belonging from the same distribution. So they might be somewhere here, here, like this. But what happens at times that while training, um, your model learns it in such a good way that your error becomes zero. Okay, the learning error becomes zero. So what you are doing is you learn something very similar, like you learn position of every data point. Okay, and when this happens, that results, that's training error will be very almost close to zero. And your if you're learning a linear regression, your R square values will be very high, 99, 98, 96, something like that. But your test numbers will be very low because you have not generalized this. You have learned everything in your training data set. So as a data scientist, or when we build a model, we want to have a lower error value, but it should not be exactly zero. We want to reach at a place wherein it generalizes well for the test and the trained data set both. Okay, now when we have overfitting, so this particular case is called as overfitting, wherein you learn everything and you get this, instead of getting a straight line, you get this exactly curved line which predicts every point in the training data set exactly as it is. So when you have overfitting, now this is a problem for us. Now how do we prevent this is the question. How to prevent overfitting, right? To prevent overfitting, there are there is something which we called as regularization. Okay, and within regularization there are three different methods there are actually a couple of other methods as well. Data augmentation is being one of them, but we are not going to talk about, because data augmentation is very specifically used. But that's also a possibility, and I'll just mention that as well. So first is L2 regularization. And then you have early stopping. And then you have dropouts. And data augmentation can also be used. Okay, so what is L2 regularization? L2 regularization is basically, first let's just talk about L2 regularization. There are different forms of, it could be L1 regularization, L2, L3, L4, L infinity. There are multiple, but L2 regularization happens to be the most popular. So in L2 regularization, we know that our loss function for the weights in the deep learning problem is represented by JW, let's say, and you want to have in the normal condition, you will want to minimize this value, right? This is what we want to do with respect for each of the W's. When we want to do the regularization, what we do is, in case of L2 regularization, what we will do is we will minimize this with respect to W, but along with this, we will penalize this with this particular value. We will penalize each of the parameters, and these parameters in linear regression are also sometimes called as beta coefficients. So we'll penalize this with some alpha value. So in some sense, what we are trying to get to is a more simpler model by choosing this thing, by doing this particular thing, we are getting to a closer, a more simpler model by making some of the weights, or you can say parameters, basically theta, close to 0. Okay, so this is it. In L2 regularization, you do the square of this and you divide, multiplied by alpha by 2. When you do the squaring, it is called as L2 regularization. In L1 regularization, what you do is you just take the absolute, and what happens if you take just the absolute, you will not what will happen is that the sum of the weights will become absolutely 0. Okay, in L2 regulation, that is not this does not happen. Every weight has some value. It is not that the parameter will go as you will something like that. It's not important. Something like that will not happen. It will be considered, but the value of that parameter will become very, very less. Okay, so if you do this, what happens to your gradient? What will happen to your gradient? You had W, and you wanted to update it with some eta or epsilon value. So you will now have this plus delta of JW. Right, this will be your delta. And if you open this, what you will notice is that if you multiply this with this, so you can have you will only have 1 minus alpha, which will be multiplied by your eta, and then you will have W outside. Then you will be left with eta and gradient of J of W. Okay, so here L2 regulation is what this is doing. If you look at this term, these terms, if you do look at these terms, what is happening is that it is multiplicatively shrinking your weight vectors. So this term is important. Multiplicatively shrinking your parameters, weight parameters. Okay. And it is done before going to the next step. So multiplicatively shrinking your parameters by a constant before performing gradient descent. Gradient update, basically. Okay, so this is about L2 regularization. You have L1 regularizations, you have L infinity regulation, LP regularization, basically you can choose. But as I mentioned that majorly L1 regulation, L2 regulation is used. In L1 regularization, weights can get in completely become 0, and because that weight will get multiplied by some value. Right, if you look at this weight, let's say weight is there, this weight gets multiplied by x1. If that weight converts into 0, this feature means that feature is not important. So sometimes when you apply L1 regularization, you can also do something as which features are important for me. So one such algorithm is uses L1 regularization is called as lasso, and that lasso regression can also be used for identifying important features. Okay, similarly ridge regression on the other hand uses your L2 regularization, and ridge regression is can also be used when you have multicollinearity problems in your linear regression stuff. So this is all about L2 regularization. Second is, after L2 regularization, the second thing we discussed about was early stopping. In early stopping, see, when we train over the epochs, right? When we train over the epochs, what happens is the training error starts to decrease over the period of time. So let's say I have this number of epochs. So basically first run, second run, third run, fourth run, fifth run, sixth run, seventh run. So 1, 2, 3, 4, 5, 6, seventh run. And you have your error here. So what happens is that with every run, you will see that your training error starts to decrease. But when it comes to validation set, validation sets generally starts with a little bit more error than compared to the training error. So you will see that it will first start to decrease, but then eventually it may start to increase. So what do we say is, at this particular point, this point is an optimal point for me. This point is an optimal point. So 4 epochs is something which I should stop. And after this, I see that the overfitting is starting to happen. Okay, so this orange line is basically validation error, and this blue line is training error. So we say, okay, we should stop early so that I do not get into overfit. Okay. So any questions here? Okay, no questions. So we can, as I said, that we can use early stopping as well. And then we have third measure, which we call it as dropout. Again, this dropout is actually very, very famous in deep neural networks. In dropouts, dropout concept comes from something called as ensemble models. Okay, are you guys aware of what is ensembling of models, or what are called as ensemble models? Anyone? Okay, so I'm gonna assume that you know what is ensemble models. So in dropout, what we do is, it's a very popular technique for the models, for the deep learning. And here what we do is we train multiple models. You know, that can be in our case, what we do is with data remains the same, but with different architectures. Okay, and then what we do is we average out all the results. And actually, I will not give you this average out all the results, but sometimes we average out, sometimes we do not average out. So we run the different models, and then we take yeah, I mean, we have to mention average out the results. Okay, so how do we do this for our model? Is, let's say I have a network which has got 3 layers. So 1, 2, 3, and this is the output. Let's just move a little bit down, and then you have 1, 2, 3, and then 1, 2, 3. Right. So let's say this is my output. This is my y variable here. This is my x1, x2, and x3. These are my hidden layers, and then you have the output. So what will happen that this will go into this here. You will similarly have this for this. And then you will finally have the output like this. Okay, in dropouts, let's say I say that I want to drop some nodes from here. In the dropout case, what will happen that some of the nodes will be randomly dropped from the network. Okay, so what will happen, probably, let's say I was here, right? So let's say the third one is dropped here, this one is dropped, and then probably in the center one is dropped, and then you have final. Right, so you can see this was your normal network. and this one is your thinned network. Okay, so you can decide that if you have overall, let's say 100 nodes, you want to decide 50% of them to be dropped, 10% to be dropped. What number you should drop is, again, you have to do, which will result a better model. You have to do it by hit and trial. But overall in this, what we are doing is start with a network, randomly remove remove some of the nodes, and these nodes could be anywhere. It could be at the input level, it could be at the hidden level. You remove those nodes, and then after removing the nodes, you run the you run through the network and you update your weights. So what happens is that when, let's say, when you ran with the full model, you got some weights for these nodes. You got all these nodes. Let's say you got W1, W2, W3. But in this particular node, what has happened is this was supposed to be there, but you are not there. So this weight will not get impacted. It will remain the same. Only the weights for this W1 remain the same. Only the weights for W2 and W3 will get updated. Okay, and next time, let's say this is not there and this node is there, so then W2 will remain the same, but W1 will get updated. And that's how you get the ensemble of different models. So nodes to be, and every time you run this dropout, like every time, if I'm running epoch 50 times, every time 50% of the nodes will be dropped, but they will be dropped from the original network, not from the thinned network. Okay, this is important, that nodes to be removed every time from the original network and not from the thinned network. This bit is clear. So if I have, how many networks we are talking about? So it's a good question. So each node can be on and off, right? So each node can have a value of either 1 or 0. Basically, weight can be 1 or 0. If it's 0, that means node does not exist and you have removed that node, basically. So if so that means you will have 2 raised to the power n network configurations. These many configurations are possible with any given network. So if you have 100 million 100 nodes, then it is 2 raised to the power 100 configurations are available for you. So all 2 raised to the n networks kind of share the same parameters for each batch. A thin network is sampled and parameters are updated. And as I said, that only those parameters which are updated are present in thin network and are updated. All and all other weights remains the same. So this one remains the same. Next time, whichever node is dropping, that weight will remain same. Everything else will get updated. I hope this bit is clear. Now, what happens in the time of testing is because in training you have trained weights. Some of the nodes can appear n number of times, so the probability of occurring a node is calculated during the training time when you're doing the dropouts, and that probability is multiplied with that weight, and then they are summed up together to get to the value. So it's just a technique, and it's not certain that, again, why we do this. But in training, let's say you have this, you had different weights. So W4, W3, W2, W1. This is your training time node. So this is during your training time, and here we look at that every time we did this 50 times and we drop the nodes, what was the probability of that node getting being available. Right, and in the test time, what we do is all these weights are present there. So what we'll do is we will have W1, W2, W3, W4. What we do is we multiply that by these probabilities of node being available for each one of them. Okay, and that's how you present it. This particular way of doing thing is called as weight scaling inference rule. Weight scaling inference rule. But as I said again, I have not read anything wherein it says that why we do that and what is the justification for doing this. Only thing I know is that when this is done, you get a good results. And all these things which we are studying, it's not something, if until unless you have decided to draw your own network from very scratch, maybe for a research perspective or something, you don't really need it. But if you have decided to draw your networks from very scratch, then all of these things are which we are discussing are very, very important. You look at all these formulas, you write functions for them, and you try to get to the answer. Okay. Okay, I think so far good. So and one last thing is data augmentation. Data augmentation is basically what we do is we generate new data set. That could be a false data set, kind of bringing in the noise. Or for example, a best example to help you understand data augmentation is, let's say I'm doing a photo classification, and also show you example in the notebook. Let's say there is a man like this. Okay, I'm trying to figure out whether he's a male or not. So there are males like this, but not all males will fit, sit in the photo exactly at the center. Some males can have photo like this, right? Now this will be corrected, but it will fail to understand this, because you understand that in this by photo you have a male pixel starting at probably this coordinate, but in this coordinate it's not happening. So then it gets confused. So what we do is we take this photo and we rotate this photo here and there by 90 degrees, 20 degrees, 40 degrees, and we start generating data. We blur this, we move some pixels, we crop this photo, we add certain black spots like this here and there during the training, so that it understands what is what. That's called as data augmentation. Any questions with the data augmentation? Dropout, early stopping?
Is there a way to validate the augmentation that is done by the
When you say validate, what do you mean? I mean,
so in general, data augmentation is like we are in. So what I mean, to what percentage does this have an impact in the results? The augmentation of data.
that can be subjective. So what you do is when you're training, but it can have a very good impact. To be honest, like I was working on some project wherein we had earlier accuracy of 62%, but when we added the augmented data, it shooted up to 74. So it can have a pretty good, decent impact on your modeling,
Okay. Okay.
and can also help you with the and in some cases data collection is very difficult. So what you do is data augmentation. With data augmentation, you are creating new images, so it becomes a part of your data. So that's how you also increase the amount of data which you have for the learning.
So in that situation, Mohit, I have a question. If
Yeah.
based on the is there a possibility that the data that when we train after augmentation can be one-sided? That is one set of information, or can be inclined towards one kind of information?
Yes, it can happen. So what you have to do is, when you do data augmentation, let's say we're going to solve a problem where we're going to identify cats and dogs. So when I did data augmentation, I should not only augment cats. Otherwise, I will have more examples for cat and less examples for dog. And my prediction for my algorithm will not be able to learn what are the features for the dogs. And it'll learn more about the cats.
Yes. So it is better the number of augmented data should be equal among all classes.
Yes.
Okay.
Yeah. Okay. Good question. This was a very good question. Anybody else has any other questions? Actually, I don't want to brag about myself, but I'm telling you, I have got a lot of experience with the data science, literally hands-on experience. So whatever questions you have, you can shoot out, and I can give you, real examples in real world. When you go out for a job, you're working for 10 years, what sort of problems happen and how do you solve them? So please take this opportunity and ask me questions. I just did the bragging. Okay. So I think the next part, if you do not have the questions, then we have next part, which is optimization. Because as we said that another problem, you are not able to have a good training results or test results, it could be because of optimization algorithm. So because you want to the idea is to have your training errors at a reasonably low levels, not zero. if you are getting zero, suddenly when we build the models, in real life, if my errors suddenly shoot up to 95, 96, we are all scared because we know that something has went wrong somewhere. In real world, you do not get such results. But when you study, when you write papers, when you work through all these things, you get curated data and you see very high accuracies. But in real life, you do not see such big accuracies. I think for the classification problems, the range would be about 65 to 80, 81. Anything above 85 is everybody is scared that it could be, the results could be possible, but we are always more alerted when we see such high accuracies, right? So optimization techniques, we have already discussed one technique, which is stochastic gradient descent. We'll not discuss this again. So that is one thing. The second thing for the optimizations is momentum based. Okay. Now, what is momentum based optimization? Now, the gradient descent which we have been talking about so far is that you have a point here, right? You start with some weights here. You could have started with your learning rate to be either very large or very small. If you take it very small, then you will move very small steps, and it will take a lot of time for you to reach to this particular point, where an optimal point which we're talking about. It will take a lot of time. Okay, so that's a problem with putting up a very small learning rate. If you have a very large learning rate, then we have another set of problem. And what is that problem? Okay, fantastic. If you are using a very large, then you can probably be moving a larger steps, and then you will move a larger step, then you will move a larger step, larger step, larger step, larger step. What happens is that you start to oscillate, and slowly your error starts to decrease very slowly, but you keep oscillating and you never reach your optimal numbers, optimal weights. Okay. So eta is again is like a hit and trial. We will set up different values. We will run n number of models. On a typical day, I'll be running, when I go at a modeling exercise, like, I've cleaned my data, I've decided on my parameters, I've created all these things, I understand what needs to be done, what needs to be done, and I have prepared my data in a format which the algorithm will take. Then my typical day will ensure that I'm running about somewhere between 10 to 100 different models in a day. Then I'll select these, then move further and on so on. So could be sometimes even more than 100. I don't know if you guys know this or not, but models like BERT, which have been trained, they have been trained on super expensive or super computational computers, and still they have taken 4 days, 9 days like this to train. And like really high machines, TPUs with big RAMs, and they are parallel processing happening. There's so much happening, but the kind of data and the kind of search they do, this optimization takes a lot of time. I personally have also run algorithms which have ran for a week or so to finally see the results. So that this is the problem which we are dealing with. And it's a basically it's a time consuming thing for a gradient descent to navigate through this region. And this is just 2 dimension. You can imagine that you are in a hilltop, and you have probably gone to some place wherein there are hills, and you want to get down. There is no road, but you have to define your own area to reach down, and you can understand it will take a lot of time. So idea behind the momentum is that how can we fasten this process? How can I say that, okay, can I take larger steps? Can I initially take larger steps and then probably slow down, or can I take in the same direction? Because you remember that we talked about mini batches. In one batch you are moving in this direction, in other batch you're moving to some other direction, and things can be when you average out it, you probably have not really moved much. So what we do is, the idea behind the momentum is a very straightforward idea. It says that if gradient across batches, if gradients across batches point in the same direction, right? then probably we could take, then probably we could be more confident and take larger steps in that direction. Okay, I'll give you another example. Actually, I've been drawing this U for a very long time, but your, it can also look something like this, wherein probably you start with this, say. So now you're gonna do very small, because you're gonna work with your eta. You will decrease your gradients. You will identify the direction. Then you slowly move your gradients. It will take a lot of time to reach here. So what this is saying, this everything is pointing in this direction. Then you can take a larger steps, and then probably you can reach there. Okay, rather than taking and identifying that what should be my learning rate and where to stop and where to start, you just need to initialize it randomly, and then you just take follow this momentum idea, and you can get to this point faster. Okay, so momentum methods, so what momentum methods are doing basically, in one line, if I have to say, they are accelerating learning. Okay, that's what they are doing. They are accelerating your learning. Now, the concept of momentum has two different versions. One version comes from the writer of the book. So version 1, there's no particular name to this, I guess. Version 1 comes from Goodfella book on Goodfellas, or I think Goodfellow by et al. A book. So according to this concept, what we do is we create an intermediate variable. Let's say we call it as V. You can call it as something else, but it's popularly called as V. And this is called as intermediate variable. And we update this variable by multiplying its initial value with some alpha, and then taking the average, and then taking the multiplying by the gradient. Okay, and once you have got this, next step is you update your weight with by adding this intermediate variable. Okay, so this is what happens in this particular version of the momentum. You calculate intermediate weight, intermediate variable by this formula, and then you add this to this. So to have a better understanding, let's say let's do a quick sort of a calculation wherein we say initial V naught is 0, and obviously your W naught is some value here, right? But because W will be initialized at some value, you can consider this as 0 as well. But let's just consider your first value. So in the first step, what will happen? We will go to this formula. So W is 0, so this value will become 0. You will only left with this value, right? So your V naught, V1, which is your first step, is only this, right? And this is with respect to the W naughts, right? This is everything is with respect to the weights. This one is clear. Now we will update this W. So we will have this one, and we will put the value of V here. So this will become W minus epsilon G hat of W. I'm just letting go of the naught. Everybody is clear about this. This is the first thing. We're just gonna iterate again and again. So this my first epoch happened. I updated this. In the second step, now what will happen? We will calculate the V2. So to calculate the V2, what we're gonna do is now we have the V1 value, which we have to multiply by alpha, right? And then what we have to do is we have to subtract this value from updated value, that is we had V1, probably we can write it like this. And if I add this value which we have got from this one, which was this one, so this equation will look like no, sorry, we have to multiply it by the alpha. So I'll say negative here, alpha minus EG, and then with respect to weights, then minus. So this is W naught, and then this will be this value, which will be epsilon G hat, and then W, this value basically. Any doubts here? So we got minus alpha epsilon of G hat gradient of W minus gradient of, we multiply the eta gradient of W1. Now what we'll do is we'll move to the, we will add this, we will calculate the W2. So W2 will be what? W2 will be this W1 minus this particular term, right? You have to add basically W2. So because negative sign was there, so I used -1. So what is happening? Okay, so W1, then this will be minus alpha epsilon W naught minus epsilon G hat W1. Right. Now, similarly, we can go forward and we can probably calculate for one more thing, which is V3. And I think the idea will get cleared what is exactly happening here. If you will look at the terms, it's good that they all are coming on the same screen. So again, this will be now V2 will come here minus epsilon of G hat with W2. So this will then further look like you will multiply it by this, where is this V2 value alpha. So this will become alpha square, right? It will become alpha square epsilon G hat with respect to weight 0 minus this then further follows by this, which is alpha epsilon gradient of weight 1 minus epsilon gradient of weight 2. Okay, now let's just focus, if you're really understanding what we are doing here, is let's just focus on first this thing, then or probably rather than focusing on these things, let's actually, yeah, we can focus on these things only. We can focus on initially this, then this, and then this. Okay, I don't really have to go to the W and calculate this because these are the three things which we want to really focus on. So you see, earlier it was only with respect to the gradient of gradient multiplied the eta with respect to weight 0. Then alpha particle alpha contribution came into the picture, and it was with respect to weight 0 and then weight 1. And then alpha became a square. Then it was with respect to weight 0, then weight 1 and weight 2. Okay, so uh, so what does this means is that what is happening is that how do I put it into the words is, first thing, if you put alpha here as 0, then it's a regular gradient, right? If you put alpha to be here 0, then it is going to be a regular gradient descent algorithm. But we are not putting alpha to be 0. Alpha value will be generally between 0 and 1. And the step size here, every time if you see, is determined by the magnitude of the V. Okay, so if you are far, if you're far from the optimal, it could be what you're doing is you are taking larger steps, and it could be a really useful thing for us. Okay, so however, with this alpha square, and then it will become alpha q, alpha 4, and all those things. So with this alpha square or with this alpha value, what is happening is you are giving a decayed effect in the momentum. You are getting a rather than you can say decaying effect is happening because of that. Okay, so because why I'm saying decaying effect, because if you see your alpha value, as I said, the alpha value has to be between 0 and 1. If your value is 0.4, then the next value of alpha square will be 0.16, right, which is lesser than the 0.4. So that's why I'm using the word decaying effect. So this brings up the decaying effect. This bit is clear. So this is how what you are doing is, so basically what you're doing is, initially you are taking a very large steps, and then your alpha value or the contribution of your eta or moving starts to kind of decay out. Alpha value starts to decay out. So here we are really putting much more effort on the magnitude, that how much and how fast we should, or in which direction we should be moving. Okay, this is the first version. The second, do you have any questions with this first version? I'll just mention here that alpha value has to be between 0 and 1. So alpha value has to be between 0 and 1. Okay, no questions. Then we'll move to the second part of it, wherein we are talking about the second version. In this, so now we were doing this wherein we had V alpha, V minus each other. Now, instead of doing that, what we do is we say V to be updated as part of V minus 1 minus alpha, not infinity, alpha. 1 minus alpha, and then you multiply it with the gradient of this, and then finally you update your weights. Okay, now one this particular thing, or let's not go into the detail of what we are doing, but let's just understand what this statement, what this equation is. This equation is called as, this way of representing is called as convex combination. Okay, so what does that means is that the accumulated gradients will always lie between V and the next V hat values. It will always lie between that. So basically, if you have a convex combinations between 2 points X and Y, or two values X and Y, then the 2 points of value always lies between X and Y. You will not have any other value greater than this or lower than this. Okay, so the question, Chitra has a question: when will you decide that stochastic or mini batch gradient descent is not adequate and would go for momentum based optimization? Okay, now when do we decide this? Is by looking at our validation scores and our training scores. So what we do is we need to study our how my validation with every epoch is changing, and then we decide that which optimization method I should use, or should I go ahead with stochastic. Stochastic again, is again, you have to understand that if the my validation score is not moving much, then we will decide, okay, let me just try with the momentum, so that probably the uh, the surface or the area or the space in which I'm trying to look out for my minimum value or the optimum results is more of a flattened, or there are too many uh, local minimas and there is global minimas. Does that answer your question? Do you understand this bit, Chitra? So basically we have to study our validation training and the test training. There's not really a I mean, these subjects do not have a particular answer that, okay, in this particular situation you will look, you will do this, you will use momentum based optimization. The reason being is that as the space increases, just imagine that drawing a 3D graph itself is such a typically difficult thing. Even if I try to draw it here, I mean, if I have to draw a 3D graph, what I'm going to do, I'm going to say something like this, right? So each observation, this is x1, this is x2, this is x3. I cannot even show you what is x4 looks like, and we are talking about millions of parameters. We are talking about a dimension which is just like you sitting in a room and you can see everywhere, and every particle is makes one direction. Okay, so that's why it becomes impossible for somebody to visualize and say that, okay, so you can only have hints wherein you just compare your training errors, and I draw training errors like this, but probably it's not always going to be so smooth. Training errors can look like this, and then your validation errors can look like this or look like this, so it can be of either shapes. But the point is, you need to understand that if your validation scores are not changing very frequently, or it's not moving, that means you are not moving in the direction which you should be moving. And if you are seeing these results in training and validation, probably what I'll do is, when I'll show you examples, I'll recall all these things and I'll help you understand what I mean. Okay, but if you get partially, then I think I have to be satisfied with this, that you understand it partially, because there is no proper one answer towards this. We, as a data scientist, I look at my training and test, and probably when I'll show you these results here, wherein these results. So now I've just run 10 epochs, but you get these accuracies here. We compare this accuracy and this accuracy. We can draw the graphs and all, and then we compare. So sometimes what happens that this will, you will see the same numbers. You will see 92 to 89. Then you will see next epoch, you are seeing a result between 80 and 70, then again 92, 72, then 80, 80. So results are oscillating between 90, 80, and then 70, 60, 90, 80, 70, 60. So I know that the oscillations are happening. That means my minima is somewhere in between that. So we are going there, coming back, going there, coming back. So things like that. Okay, so we'll see, we'll talk about all these things. But this version or second version is clear that what this is all about. We want to, in this, magnitude of gradient does not keep increasing. In the previous version, the magnitude of the gradient keeps increasing, whereas in this version, the magnitude of gradient does not keep increasing. It's more about the direction rather than and we control the magnitude of the gradient. Okay, whereas in the previous one, it's more about the magnitude, and obviously the direction is not put that much effort there. Okay, here we are kind of restricting it. So we are good so far. So with this, I want to bring, so momentum is clear basically. I mean, in totality, if we have to say that somebody comes back to you and say that, do you understand momentum? You should be able to say that, yes, momentum is basically a way of optimizing, wherein you try to take larger steps in the direction where all the batch says that the slope is in the, most of the batches says that slope is in direction. So you try to take more larger steps in that direction. So that's why the name is also given momentum, right? If you're going down the hill, you will have a more momentum. If you start running, it gets very difficult to control yourself and stop. It takes a lot of effort to stop if you're running down the hill, right? So that's why the momentum is talking about, that I will start automatically taking bigger steps as I go towards my optimal minimum value. Okay, now momentum notion is fine. With this, I'm going to introduce another notion, which is called as next notions, which we should be talking about is and then three things we will talk about, and then we'll probably go to the other section. So adaptive, or maybe not, will not start with okay, we'll start with adaptive learning only. So adaptive learning. Okay, so what is the idea behind the adaptive learning is that when you are building your networks, right, some of the features x1, x2, x3 could be 0, right? That means some features may appear sparsely and do not have enough samples, or maybe you do not have enough samples to update weights through gradient descent, because for the features wherein you have zeros, the gradient descent will not happen, right? Your derivative will not happen. It's a constant, so you will get a 0 and it gets multiplied by 0. So when you have a sparsity in your data set, let's say x2 has a lot of sparsity, so it has most of the time it's got 0 0 0, but in training set it has ones. It can happen that in your training set it will have one. So in training it has zeros, in test it has one. So that in that case you will not be able to learn that behavior, or you'll not be able to put any emphasis on this particular variable or this particular value of the x2, because you didn't ever learn a value for this because of 0 being present here. And this kind of or rather so there is a problem like this, and adaptive learning helps us to deal with such problem. So what is the goal of adaptive learning is, can we have a different learning rate for different weights? Can we have different learning rates for different weights or parameters? And when I say weights, I'm talking about features. So for features which have got more sparsity, can I have a different weight for them? Features which have got less sparsity, can I have a different weight for them? Okay, so that's what the adaptive learning is all about, to give emphasis or adaptive learning for different features based on their sparsities. And there are three different ways in which we can achieve this. One way is called as an algorithm, which is called as EDAGRAD. Okay, so in EDAGRAD, what we have is we focus on accumulating the gradients. And we do, let's say we have G, we want to update this G, this gradient with the you get the weights from the loss function. And what you do is you have this R, which is accumulative gradients, which represents accumulation of the gradients. And what you do is you take this R and you do a dot product between your gradients. Okay. Uh, so this one is called as, there's a special name for this. This is called as this one here is referred as element wise product. Okay. So basically every term in your gradient gets squared. Okay. So basically every term gets squared in your um, in your gradient matrix. And this R is also is basically secondary, second order statistics. And once you have calculated this R, you update your weights by saying W epsilon upon, you have this delta plus under root of R, and then you obviously G is what you have to multiply with to reduce the number. So again, this concept is coming from the momentum itself, but what we are doing is we are kind of upgrading this momentum idea by saying that they're going to be weights wherein I need to modify those weights, and those weights will get modified because of this R secondary component which we are doing, and because of this G which we are doing. And delta is like a constant which I'm adding to ensure that even if the R is 0, there is some fraction which I'm going to do with the learning rate. I'm going to change some learning rate there. Okay. So weights with very few updates will have, with this formula, what happens is that the weights which have got with very few updates have small accumulations, and is like the same weights which have got high, basically if you look at this, for small accumulations you will have larger learning rates basically. So I can say for small accumulations, or you can say inversely proportional to high learning rates. Okay. So wherever your R is, where your weights are very, very small, or are zeros, you will still have a delta value. You will still give some learning rates, and then you will add that to it, and you will have a higher learning rate for those. For the other ones, you will have a lower learning rate. So with EDAGRAD, there is a problem that learning rate decays aggressively because of this particular thing which we are doing here. So when the learning rate decreases aggressively, ultimately what happens is that you started with some number. Let's say you started with, I'm just writing 10, but learning rates are again very, very small numbers, but I'm just starting with 10. Let's say we started with 10, initially it dropped to 7, then it dropped to 5, then it dropped to, let's say, 2, then it dropped to maybe 0.5, and ultimately it became 0. So then what will happen if at the moment it becomes 0, you're not moving anywhere. You are just on the same space and your algorithm is running, right? So that your gradients are not getting updated. So that's a problem which we have with the EDAGRAD. And so what we need to do is we need to mitigate this problem. It's also a very fantastic algorithm, but here the magnitude and the decaying is becomes a problem if you're taking a longer time to reach your end goal. Okay, your optimal solution, then because or automatically your learning rate will become 0 and becomes a problem for us. So the solution for this one is to implement something, second thing which is on the second version of momentum which we discussed, and that's called as RMS prop. So this algorithm, what it does is, again, you have G wherein you want to have a delta of L with respect to W. You have R. In here, what you do is, so if you remember in this, I'm going to put a concept wherein I don't want alpha to suddenly become 0 or my eta to become 0. So I'm going to use this convex combination and implement it here. Okay. So when I implement it here, what I'm going to do is I'm going to say P of R plus 1 minus rho. So sorry, this is not rho. This is not P. This is rho multiplied by R plus 1 minus rho, and then G got G. Okay, so this is rho, right? This is called as rho. So what happens is you kind of limit your R. It's not gonna become 0, or it's not gonna become magnitudely very, very high. So that's how you that's what one change happens with the RMS prop thing. Any questions in this? But then again, your weight gets updated with exactly the same formula for the RMS prop as well. So main idea here is to limit the magnitude with respect to convex combination. And then finally, the third thing which is very popular is Adam. And I think at least in last 2-3 years, I have hardly used. I mean, for experiment perspective, I would have used EdaGrad, RMS. Again, you do the experiments, you build different sort of models with different, taking these optimization algorithms for the adaptive learning. But among all these, Adam is one of the most successful, because what Adam does is it takes components of both RMS as well as the EdaGrad and implements it. Okay, so here you technically what you do is you have G. Why I'm writing this again and again? Okay, that's fine. And then you calculate one parameter S, which is going to be this one, G. And then you also calculate a parameter called as secondary parameter. Certain statistics is called this. So this is rho 1, this is rho 1, this is rho 2 R plus 1 minus rho 2 G dot G. Okay, so these are the things which you do. So technically your weight should look like this in then when you update it, it should look like this: epsilon bracket sigma plus under root of R, and here you multiplied with S. Okay, because you're calculating. So here you are calculating 4 new parameters which you are using. But there is something which technically this should happen, but when they implemented this algorithm in Keras and in other things, what they did is, instead of doing this, they, instead of calculating S directly like this, what they did is they modified this formula, and this calculated S hat is S upon 1 minus rho 1 raised to the power T, which is your test thing. Then rho hat was calculated as rho upon 1 minus rho hat divided by T. So what does why they did this is, it apparently seems like that this is apparently this way of doing and calculating S is apparently done to take care of bias. Okay, so your formula then is, so you're, instead of using this formula for weight updation, what we use is this one. Under root of rho hat and then multiplied by S hat. This is the formula which we use in EdaGrad. So if I have to consolidate everything, so in RMS prop, you are not getting the benefit of accumulated gradients. In Adam, you are not in EdaGrad, you are not getting the benefit of dealing with features who are very sparse, where the sparsity exists. Whereas in Adam, you take care of both the things. In Adam, you're not just taking care of sparse matrices, but you're also taking care of accumulated gradient problem as well, accumulation of the gradient problem as well. Okay, so these are the things which we use. You will see how we use it. It's just that I don't see people asking these things, but obviously if you go into research, if you want to study further, these are probably the very first baby steps for us to know. But if you talk from a technical perspective, most of these things for me is an hit and trial. As a data scientist, I will select, obviously it's a, when I say hit and trial, it's also a guesstimate, right? I have some direction and then only I try that. But people who do not have directions, they can also it's just about spending your computation resources, so, or the time it will take. So some people just run a grid search wherein they will run first model with the EdaGrad, then second with the RMS, then with the Adam. They will try different epochs, they will try different alpha values, they will try different learning rates, and then it'll it'll be like a huge grid wherein they will it'll be a multi-dimensional grid. For each cell they will pick one value and then set of values and then run the model one. So in one go, they'll be running like 100, 200, 300 models. Out of those, they will select the model wherein they have got the best results. Okay. So that's what people will do. Any questions so far? Maybe you can tell me how bored you are on a scale of 0 to 10. 10 being super bored. Okay, so let's just do one thing. Let's first we want to discuss the we'll say the reconnect. We wanted to discuss the research part of it, but what are the sections where people are doing the research? But rather than doing that, let's first walk through the example here, and let's just understand what we are doing step by step. So here is a data set wherein we want to do a bifurcation or classification for cats and dogs. It's already an available data. This problem was also given on Kaggle as a competition. What we're going to use is, there are two main frameworks wherein it gets easier for to implement um, deep learning algorithms. One is Keras, one is PyTorch. PyTorch is being worked upon by, I think Facebook, and Keras is being developed by another organization wherein they build this popular. I am very comfortable with Keras, not really comfortable with PyTorch, but it seems that PyTorch gives you a little bit more flexibility when it comes to developing your own layers. Okay, but in this example, we are using Keras. So TensorFlow, we are loading the modules which we want. Okay, here we are loading the whole module itself, and then we are just giving it an alias name. Here we are saying from TensorFlow, I just want Keras. Within Keras, I want layers. Okay, this is a place from where I want to read my data set. So when I read this data set actually technically comes in this folder. Right now, when I get disconnected, that whole file gets washed away because it's a temporary place. If I want it into the nice place, then I have to attach my Google Drive with this and then save that file in that. But then it takes a lot of time to read. Not really lot of time, but yeah, that takes a time. So what we do is we download this file. This is a zip file, and this is basically a command line command. If you want to run any command line command within the notebook, you have to use this exclamation mark. Then I use this I unzip, and then I look at whether the file got downloaded or not. So this was the zip file. It had this pet sizes. Within this pet sizes, there were further folders. So I can check what were the folders in the pet size. This was cat and dog. If I have to show you on my local system how this, after I downloaded, how this looks like, then it looked like yes. So this was the zip file which I downloaded. This was the pet images folders, and then I had cats and dog. Generally, you will have like this. You will have different folders for images which belong to that. This is how it gets easier. So you can see there are different cat photos I have. Some cats are really cute. So a lot of cat photos we have. We have about 11,749 photos of only cats. And then if we go to the dogs, we have some dog photos, and you can see the shape and size of the dog photos are also can be different. So there is also, we have to do something about it. So if I select all of them, we have about 11,675 dog photos. So almost equal number of photos we have for dogs and cats. Okay. Then what we do is basically there are some images which get corrupted. Here we are just going through each folder, reading the file, and see if we are able to read the file or not. If we are not able to read the file, if this says that all the bytes are not available for that particular photo, we are just removing it from our path basically, and kind of we are deleting those files. So we deleted about 1590 such images when we run this. Okay, so now out of this 11,000, 22,000 images which we had, some 1590 were corrupted, so we are removing those. Next is we convert, when you run the Keras, you have to, this information will generally be provided with the dataset. So I knew that my images are of size 180 by 180, 180 pixels by pixel, so length and breadth of the pixel. So you can imagine 180 multiplied by 180, that many pixels you will be getting. So how does an image is dealt with in is very simple. So where did I keep my digital pen? Okay. So let's just say that this is a nice that I have kept this. Let's say this is image area, and each box represents a pixel. Okay, let's just say that each box here represents a pixel. So when I say 180 by 180, this means 180 pixels this way, 180 pixels this way. Okay, that's how my image looks like. And you cannot pass image just like this. So what we do is we convert this image. We have to convert this image into a matrix. You don't pass one image at a time. You have to pass a bundle of images at a time. So what we do is we take this first row of first row, okay, and we can either stack it in, let's say this comes like this. So this is first row. Then we take this second row and we stack it next to it. Then we take the third row. And then we stack it like this. So you can imagine that if I have got 28 by 28 image, then I have 786 columns, right? And then I finally have one more column which will be my target variable. So this will be my target. Will it tell me whether it's a cat or a dog? And whole row represents the pixels. So if you have 180 by 180, you can imagine that how big my data frame is. We can probably check the size of that data frame. Okay. So then you have second image, probably second images of the dog. You pick each pixel, you attach it row by row, concatenate this. You can concatenate like this. Some algorithms you can, you need to stack it like columns like this, and then you need to pass your labels separately. So it could be either stacked as a row or could be stacked as a column. I think row ones are rather more popular than the column ones. Okay. I hope everybody is clear about that. What is the significance of this 180 by 180? If you select, let's say your image is 240 by 240 and you select 180 by 180, understand that you're cropping your image and you're losing some sort of information in that particular case. If you are making bigger than that, then what will happen? You will have a blank space. Okay. So let's say there are no more pixels in this region, but because I said 180 by 180, however, this image was not 180. This was only, let's say 100. So all this thing will be blank. Okay. So you will have a blank images. I mean, no pixels basically. So you need to pad and all those things you need to do. Okay. So coming back here, this is a standard way, and I'm selecting my batch size. We talked about batch size. It's impossible to pass all 11,000 images or 22,000 images directly into the data set for the training. So what we do is we're going to decide a batch size. This converts your image data into a directory from a data set into a dictionary, and basically directory or dictionary you can say. And then these are some of the parameters that I want to have a validation split of 0.20. 20% of the data will become validation set. This is your training data set, and all these things are happening. So basically we are preparing the data here, test, train, and the validation data. So you can see these many observations are found. There are too many classes here, and this basically is talking about what size we have. And then some of the photos we are picking up and we are visualizing it. So you can see first image is a dog, cat, cat, dogs, cats, dog, cat. And as I said that, just to give you an example of data, we don't really need it here. Another reason for having a data augmentation is that probably all photos are clicked like this. Probably cat may be slightly like this. So have such examples. I'm gonna create a data augmentation. Again, it's a very simple deal. You just need to tell how much, if you go to the Keras documentation, pretty straightforward documentation, and you can read everything about it. So you can say get started, and here you can read about all these examples. So you're just telling that you need to flip this and then random rotations by 10 degrees. So once you do all these things, you run. So you see the same photo, just one photo I'm picking up, and there has been some changes made to this photo. So this photo is got rotated like this, then this. So randomly same photo has been rotated multiple times. And there are other things you can do. There are about 9 different ways in which you can create an augmented data, wherein you can put some blank spaces, you can blur the image, you can grayscale it, you can have a different color to it. All these things can be done as part of the data augmentation. Next is when you do the data augmentation, you can understand that this is colors, right? And colors value lies between 0 to 256. And some colors will be given more value than the other one because of the numbers, the weights. When they get multiplied by the weight, it will be a bigger number. So what we do is we bring them on a 1 scale, and that is what we are doing. We are doing a standardization here. So that's how the standardization happening. We divide by 255 and we get the standardized numbers. 0 is not considered here, so that's fine. And then here you are prefetching your data. Prefetching is just to ensure that there is going to be some buffer in while you are running it. Okay, so some data will be quickly fetched and you will not have any problems. Now, because this is an image problem, I'm going to run a convolutional neural network, but you can understand that batch normalization is happening. You see activation function we have applied, which is a ReLU function, right? We talked about the ReLU function. Padding and strides, you don't really need to know about it because they're very specific to uh, convolutional neural networks. Then you see I have done the data augmentation as well here. And you can see that layers of activation, which we're talking about, all these things are here. Then what else we talked? We talked about the sigmoid function, the softmax function. Softmax function is basically when you have multiple classes. We do not have multiple classes. We only have 2 classes, sigmoid. But if the same code can be used for multiple classes, if there was another class, I just need to read the data. And softmax will give me the probabilities for all the classes. The one which has got higher probability, I will select that as my class. Here, I know that there is too much data, so I'm gonna do the dropouts as well to ensure that my overfitting, I can initially avoid it. And once I have done all these things, you can see the final layer is about the dense output, and you get the output. Your model will give you the inputs and the output which you have got. If you do make through this model, then this you do the model summary, or you can say utils.plot model. This is the architecture of my model. Okay, it's going to be huge architecture, but this is the architecture of my model. So you start with input layers. Second is the sequential. Then there is the rescaling which we are doing. Then one convolutional layer comes in. Then we do the batch normalization. Then the activation happens. Then second layer of convolution happens. Then the second layer of batch normalization happens. And how many parameters do we have at the each point of time? All this is the convolution neural network. Okay. This is a self-designed network, so that's okay, fine. But you can also have a predefined convolution neural network. In that case, you will not have such a big algorithm. You will just have one function name, which will be stating that you want to run a convolutional neural network. Most cases, if you use this direct, algorithm, the in real world, at least you will not get. You do definitely need to make some changes or add, subtract as per your problem statement to get a better results. These things I've only done because when I did the convolution layer, it threw me some errors stating that these packages are missing. So I downloaded these packages. In this particular section, what we are doing is we are going to say that we're going to run 10 epochs. Minimum people will run 50, 100, 200, 2000, 3000 epochs as well. But in given the if I have to say, the best I have run is about 100, 200 epochs. I have not gone beyond that, but there are problem statements wherein you have to run that much. Okay, there is a concept of callbacks. That means when I'm running the model, if I'm going to run for 100, it's going to take about 2 days, 3 days. And if for some reason my system stops or my algorithm stops, I do not want to restart from the very beginning. So what I do is every layer which I build, we talked about these layer things here. Yeah. So every time I come back, I update my weight. Once I update my weight, I save that. So that is what callbacks is doing here. So I make a model checkpoint. That means if my model stops at a particular epoch, I will have that file with me. I will rerun my model by loading that file first and then running the model. The best thing about the networks is that networks is nothing but a collection of nodes, right? So I can connect any node with any node. Basically, you can have there's a network called as BRU. There's a network called as HAN. So it has got some nodes which are left. These are the weights for the nodes. I can attach my further layers into that. Just directly start preload this model. Maybe this is a BERT model. I load the BERT model and start using and putting across my layers further down this line. So I can, from pre-trained layer networks, you can create your own networks or attach your own networks. This is called as learning, transfer learning. Okay, somebody trained their models on certain set of data, and then you started using that from going forward. And then finally, I compile my model. I'm using an optimizer. I said Adam optimizer. This means 10.0003, 0.0001. So my learning rate is very, very small here. Okay, I can either give it like this, or I can also mention it like 0.001. Okay, that's what this represents. Generally, as I said, learning rates can be very, very small, but the smaller value you pick, the larger time it's gonna take. and it is recommended not to take larger values. Generally, minimum values people should try is 0.1, 0.01, 0.003, 0.0000, like 4 zeros, 5 zeros, 8 zeros, like this people try. And because this is a binary problem, we now know what is binary cross entropy function we have to use. And matrix, we are going to use accuracy and not recall or F score, because we went through the data, we know that the number of examples for zeros and ones are almost similar. Then we run this model, and you can see these were the results for my model. Initially it started with 66, validation 51, so kind of an overfit. Then 78, then the validation became very high. So this is an example of some sort of, you can say, underfit. Then you see, then overfit happened again, so you can see a lot of overfitting happened. Then it started to stabilize, and we started to getting a decent results. Okay, so in just 10 epochs I have started getting 0.93 accuracies, and validation was 0.92, 0.90. And then I just picked a random image from the cats. I know it's a cat, but I just wanted to check how my model is doing. And if I run this model, it tells me, you can have any sort of output, but this I presented output. This image is 43.93%. Okay, 43.93% cat and 56.07% dog. So this particular one, I think okay, we probably have to rerun this. So we were unlucky. They hear it saying more, it's a more of a dog rather than a cat. But generally you will find, because the accuracy is so high, so you will find that move for most of the examples, it will clear cut tell that 80%, 90%, 92% chances are that this is a cat and this is a dog. Okay, so this is how you build your models. And obviously, as I said, technically there could be a lot of other things which we have to do as part of this layers. And then there are 200 different neural networks as of now, and you can try a lot of other things. Okay, okay, so we'll move to the last section. Does anybody has any other questions from this section? Okay, no questions. Then we will
Mohit ji,
yeah.
I have a question related to the difference or similarity between adaptive learning and transfer learning.
Okay, adaptive learning is a different concept than the transfer learning. In adaptive learning, what we are trying to do is we are trying to say that the weights wherein the sparsity is there for each, when the sparsity is too much, then we should give a weight based on that understanding. Whereas transfer learning is that, let's say I have to learn, I want to build like for now I'm doing a project wherein I have to learn the word embeddings for the legal documents. Okay, now legal documents have a set of words which are very particularly used in legal language. You don't use those words in a regular day-to-day life. So but they also use English. So what I do is I do not have to train or vectors for my English words. What I do is, there is already people who have already trained their BERT on such English data set by scrapping all of Wikipedia, and they have created that context and they have created those vectors for me. So I pick up those vectors, and I for English I've got that learning or the weights for the English words I've already got. All I now need to do is I need to push my data and then train the rest of the words which I have. So this is transfer learning. You have already learned, and then you are just using that learning into your data set. Whereas in adaptive learning, with this learning also, you can say I want to have an adaptive learning. I want to use Adam as part of it. I want to use Adagrad as part of it. So that if there are in my data set, if there are words which are very, very sparse, then there should be a different weights given to them, because they probably can appear in the training set. Does this answer your question? Do you understand what I just meant?
So adaptive learning is more about adjusting the weights in order to reduce the overall loss that is incurred.
It is what you said, is that is what adaptive learning is. It is about adjusting the weights per the sparsity of a feature. Okay, whereas transfer learning is all about training the whole model. When somebody would have trained the model, they probably would have used. So adaptive learning is more about optimization, whereas the transfer learning is all about the whole model building concept, learning the whole idea behind it.
Even like this transfer learning could also be used to update weights of the new scenario that we're considering, right?
Right.
Okay.
So yes, but there is you are already getting a set of weights already trained, but when they are training this, so let's look at this. If you're still able to view my screen, then if you look at this particular one, see, this is a model which I'm building. While I'm building a model, I am using this function, which is where is it? Where is this? When I compile it, when I compile, I'm using Adam, right? This is adaptive learning happening, right? It's gonna take note of, because there's an element of Adagrat as well as RMS into this. So I am doing that. Using it. Now, once I have trained the model, somebody can pick this model and use it for his further learning. That's transfer learning. And in only this bit is adaptive learning. It's specifically only about optimizing the weights, whereas model is a much bigger concept and talks about every other thing involved.
Okay. Thank you. Thank you, ma'am.
Anybody else has any other questions? Shoot. Okay, if not, then what we'll do is we will just move to the last section. Okay, and probably I'll share this because there's a lot of wordings here, but we'll talk about the majorly about what we are seeing here. So let's make it a full screen. So research areas in deep learning in data science are too many research areas. Data science touches computer science, it touches the hardware, it touches the algorithms, it touches the statistics, it touches the data part of it. So there are too many areas wherein you can do the research. Majorly, deep learning algorithms is something wherein a lot of research is happening. Deep learning has given us astonishing success rates, especially in the neural, natural language processing. So we want to learn, why a particular network gives us a best results. You can design a new network. You want to understand how to verify the deep learning is performing well, the task what it is performing, understanding how it works and all these things. Because although mathematics is there, all the chain rule is there, everything is there, but you can imagine if I'm going to add 200 layers, it becomes humanly impossible for you to understand what is happening inside it. Okay, so that's one area people are trying to understand and bring up things wherein it makes much more understanding, how we can understand neural networks. The second area is computing systems for data intensive applications. We are today are having GPUs, FPGAs, and TPUs. For example, the algorithm which I was showing you, for one epoch, the estimated time for my system, which I said is a 32 GB system, it was showing me time for 1 hour, whereas this it did in just 123 seconds. So you can imagine how much, and this is just DPU. I have not gone into TPU and all those things, and these are not CUDAs and all those things. But even having those, even if I have those things, we still have a problem wherein we want to understand how we can modify our computer designs or how we can modify our algorithms so that this whole process becomes faster. Okay, so how we are talking about fast data accesses, we are talking about applications, event tasks, and while we do all these things, we also have to think about energy efficiency. Okay, so this is also a very well researched area, and there are a lot of papers you can find around this. But again, a computer scientist is a much better person to do this, and there are a lot of people who are doing this. Inferring from noisy or incomplete data. For deep learnings, we definitely need a lot of data in real world. No matter how much data we have, it's always messy. And I give you in writing, when I say messy, it's always messy. So handling this, how do we deliberately handle this? How does noise impact um, uh, my machine learning algorithms or my deep learning algorithms? How I can ensure for example, there is this problem. You must have seen these funny things wherein people make fun of artificial intelligence, wherein this is a dog and it's actually not a dog, it's a muffin which has got some chocolates chocolate chips popping out, right? And your algorithm is saying that it's an AI. So all these called as adversarial attacks. These are all noises. When we implement models, there are there are people sitting out there who push such information into our hack our systems and push such information and ensure that our machine learning models do not perform well, or take what we have trained, they take it out. So how do we implement, ensure that this machine learning is able to separate this noise and have a better accuracy or understand all these things? Is a very very advanced area, especially in deep learning. There you will find papers on adversarial machine learning attacks. So that's a active area. Trustworthy AI is something which is after the Facebook things, and there are other organizations which have used data in not so professional ways. A lot of laws and things have come into the picture, how these agents or should talk, and this is still of a debate, but I think there are people are making progress here, this is a hot topic, especially for the governments. It's a very very hot topic because now these days, a lot of models people are going, a lot of startups are going to the government organization and they are saying that we can implement this, we can help you with this, especially with the traffic lights, identifying people, tagging them. I think very well advanced things are being done in China. In India also, we are implementing a lot of things. This is something which is um, still kind of a debate, but yeah, people are making a lot of research here. Autonomous vehicles, I think in US there is still a debate going around with around this particular deal, that if accident happens, who will take the responsibility? How we can say that, okay, whatever your car is taking a decision is still a trustworthy thing which we can trust, and we can absolutely certainly say that he will take a correct call. Because there is still problems wherein there was a thing happened that this Tesla car was going and there is sun rising and it thought it's a red light, so Tesla car actually stopped. But you can override it, so it keeps showing you that red light, red light, red light. So how do you take care of such problems and things like that? So there's a search. Privacy is another area, um, and then there is ethics. About the ethics, I think ethics is something which I have not been very uh, what do you say, fully connected with, because if you're talking about the privacy, then ethics goes hand in hand. So it's a more of a personal uh, liability of an organization. But again, there are people who are doing some nice, I've read one or two nice papers around this. People are searching and how to define that, how what all will fall into this and stuff like that. So these are some of the research areas which people are which you can explore. But the overall research has a particular direction to it. What you need to do is you need to first identify the problem which you want to explore or solve. And when we say research, is not just always about getting the solution. So that's what I'm trying to mention here. You then need to ask a question to yourself, that what do you want to focus on? Do you want to focus on the engineering part of it, or you just want to focus purely on the research part of it? Engineering will involve deploying a new algorithm, infrastructure, how to speed up the data access and things like that. Whereas pure research will involve maybe a new loss function, or a new algorithm altogether, new data architecture for neural network altogether, and things like that. That will be pure research. Then you then have to do the perform literature reviews, look at the strengths and weaknesses of the methods. You can look into that. You can design your proposed solution and implement a baseline prototype. And then obviously iteratively, if you understand the second part, then you iteratively develop your solution around that. You do your research around that. Okay, I think that's it. That's what I had for today. Thank you so much. I will now stop presenting, stop sharing. If you still have further questions, please do let me know. I'll be happy to answer. If you find that today's session was too much, you go home, you sit, and you think about it. Question or two pops up. You can write down an email to me. I'm just gonna give you my email address on the chat, so you can drop an email, or you can probably go to LinkedIn. Connect with me over the LinkedIn. That's a better idea. So I'll just share my LinkedIn address with you. You drop me a note there, and I will try my best to help you and get the answer. Okay, so this is my LinkedIn profile. So you can connect with me over the LinkedIn. That's it. Thank you so much for having me and giving me the opportunity to bore you guys. Yes, it's good, but yeah, I can understand. I have been on that side, so it can be overwhelming, and I know it's overwhelming. But everything starts with every difficult subject starts with the fact that it's very, very difficult, and then you just give yourself time and you revise it, you just recall it, and hopefully you will progress. And I hope you liked what I presented today. Thank you.
Thank you so much, Mohitji, for your interesting session. I must say it was, although it looked like it was extremely elaborate, but it was extremely informative also. We would actually like to thank our colleague, Dr. Jansi Rani, for introducing you to us.
Yes.
Thanks
Thank you
to
so
you
much,
for,
Jansi.
yeah, thanks to you for accepting our invitation and for being here with us today. Right from clearly explaining us the roles and responsibilities of a data analyst, data engineer, and a data scientist, how they are different from each other. And apart from that, what are the skills that are required for these jobs, right? So that was extremely useful. And your detailed explanation on the mathematics behind various ML techniques are extremely outstanding. And a walkthrough on the classification of images between using different models actually made the talk a lot more interesting. So on behalf of the organizing team, and we would like to thank you wholeheartedly. And we will also like to thank our HOD and the SSN management for giving us this opportunity to have this nice, wonderful interaction. And I also thank the participants for your participation. Thank you, everyone, once again. I'm sure everyone, the entire 3 sessions, I'm sure every individual participant would have taken at least something back from this, from today's session. So thank you so much, Mohitji.
Thank you. Thank you so much. Thank you, Priyadashni. Thank you, your honorable HOD. And thank you so much, Jansi, for introducing. And wish
Thank
you
you
guys
so
good
much,
luck.
Sir. Thank you so much, Mohit. I have been sending so many mails to you. You have responded.
No, I was actually feeling very, very guilty because my my workload is very high. I just got promoted, becoming a team leader.
Oh, very nice.
Yeah. So
Congrats.
suddenly too many things came into the picture. I need to, and I was not able to reply to you. I was thinking that she must be
No,
thinking whether I'm
we used to
available or not.
send so many mails, and we have requested so many things from you. And you have actually all the topics you have handled today. Only after interacting we have fixed the topics also.
Right.
So that was great. You helped us a lot.
Okay. Thank you
Thank
so
you.
much. Okay. Okay, guys. Bye bye. We'll probably speak later.
Sure. Yeah. Thank you so much, Mohit.
Okay, Manisha. Bye bye.
Yeah, bye. And I just want to inform that the participants, we have shared a feedback link in the chat box. We request you to kindly fill it for easy preparation of the certificate.
Yeah, the feedback form is again posted. Please fill in the feedback form.
We also have streamed live the entire session, all the 3 sessions today. So if you would like to have a relook at the sessions, we have it in our SSNC CSC ICC Ideas CSC YouTube page. So you're free to have a look at it. Thank you, participants. Hoping to meet you all in another interesting interaction. If you have filled the feedback form, you can leave. Thank you.
Thank you, ma'am.
Thank you.
மனிஷா
பாலா சார் சொல்லுங்க.
செஷன் க்ளோஸ் பண்ணிட்டுமா?
ஓகே சார்.